Welcome to my ultimate AP Precalculus practice test. What I did with this new series of videos is I took an official AP Precalculus practice test and I ever so slightly changed the problems around so I wouldn't infringe on copyrights. So here's problem one, and this would look like a problem one on an official AP Precalculus test. Consider the polynomial function q of x equals negative 2x parentheses x minus 3 parentheses x plus 1. What are all intervals on which q of x is greater than or equal to 0? So what I need to do is I need to imagine what the graph of this looks like and imagine where the graph would be positive or above the x-axis. All right, so what do we have? We have something times something times something. Whenever you have a problem like this, you take the x values in each parentheses and each factor and you multiply them together. Negative 2 times x times x times x is negative 2x cubed. The rest is, you would FOIL it out and you get blah, 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 and it doesn't really matter. Why am I doing this? Well, this gives us the behavior of the graph, what the graph is going to look like. It's cubic. It's negative. It's going to look a little something like this. Now, that's part one of what we're dealing with. Part two of what we're dealing with is I do have three factors. And if I care about when it's positive or greater than or equal to 0, don't I care about when it's equal to 0? I do. Let me answer that for you. I do care about when it's equal to 0. So if I were to imagine that each factor is equal to 0, like, negative 2x is equal to 0, divide both sides by negative 2, you would get x equals 0 for this one. If I were to imagine that this is equal to 0, I'd add 3 and I would get 3 for this one. And if I were to imagine that this is equal to 0 and add or subtract 1 from both sides, I'd get negative 1. So my zeros are 0, 3, and negative 1, not in that order. Now what I'm going to do now is make a sign table or a sign chart, as some people might call them. Now this sign table takes my zeros and it also takes my graphs and puts them together and makes me find out where this guy is positive. I cross this graph right here in red, crosses the x-axis at negative 1, 0, and 3 in that order. So negative 1, 0, and 3 in that order. I know the graph looks like this. So if the graph were to pass through this line, it would start looking out like that, and then at some point bottom out here, go through the 0, and then come up, and then come down through the 3, and then there you have it. Okay. Why does this matter, you ask? Well, I care about when this is positive. This is my x-axis. Everything above the x-axis is positive. So it's positive here, and it's positive here. I also care about when it's equal to 0. So it looks like it's going to be positive above the line from wherever to negative 1. Well, we don't say wherever. We say negative infinity. Now, I'm writing this out in interval notation because of the way this is given to us. So all the way from negative infinity all the way to negative 1. Now, here's the thing. At negative 1 and exactly at negative 1, it hits the x-axis, which means at negative 1, it's a 0. So if I want to include something in its interval notation, I put a bracket around it. Instead of saying something like and, I say union. And then now it's negative, now it's negative, now it's negative. Then it hits 0 at 0. So at 0 and including 0, it's going to be 0. And now it's positive, 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 positive. And then once I make it to 3, it's 0 again, so I include it. So my answer is negative infinity, and you never put a bracket for either infinity because you can't include an infinity. It's a concept, not a number. Come on. Negative infinity to negative 1, union 0 to 3. Just like that, the answer is D. Thanks for watching. Hope this helps. The function g is given by g of x equals 7 times 16 to the x power. Which of the following is an equivalent form for g of x? All right, so what they want me to do is they want me to rewrite this guy to make it look like this guy. Now, in these examples, it gives me like these 3's, and if you're wondering, where does that 3 come from? I don't know. Let's get rid of them. Don't need them. Now I need to worry about 7 and 7, and here's 7. So I'm not worrying about changing the 7 to anything. Maybe if that 7 was a 9, they'd be cute and call one of these 3 squared or something like that. But it looks like what we're doing is we're changing 16 into 4 to the something power. So I could rewrite 16 as 4 squared. Now I'm putting parentheses there because you'll see in a minute. Now 16x is not, that. I need to do a little bit more. I need to attach the x. So now what I have right now is 7 times 4 to the second power to the x. Well, that's not an option. But oh, wait a minute. When I have something in parentheses and I take that to another power, when I have a power of powers taken to a power, I think I said that right, you multiply the exponents. So I could rewrite this as 7 times 4 to the 2x. So g of x can be written as 7 times 4 to the 2x. So D is my answer, baby. Hope this helps. Thanks. Like and subscribe. The figure shows the graph of a function h. The inflection points, and if you're like, what the heck's an inflection point? An inflection point is if you have a graph. An inflection point is where that graph changes concavity. So you're concave up, you're concave down, and you're where it changes from up to down. Or vice versa, it could change from down to up. Doesn't really matter. I just drew this picture because it looks like that. And extrema, and if you're like, what the heck's the extrema? Well, an extrema is the very maximum of an area or the very minimum of an area, depending on which one. Extrema is just fancy like extreme. Anyway, the inflection points and extrema for H are labeled. So you're an inflection point, you're an extrema. You're an inflection point, you're an extrema, you're an inflection point. Let A, B, C, D, E represent the x coordinates at those points. Got it. Of the following, on which interval is h decreasing and the graph of h concave down? Well, first off, decreasing is where anywhere on the graph it's going down and to the right. Now, it could look like this, it could look like this, it could look like this. All of those are going down and to the right. You are decreasing here, and you are decreasing here. You are increasing from B to D, so that's not going to be an option. Anything from B to D is not going to be an option. Also, it's concave down. Now, concave down look a little something like this. And in this case, the only part that looks a little something like that is from C to E, and maybe forever on after that. Look at that perfect line that I drew. Now, in this case, the area that fits both criteria is going to be from D to E. D to E is decreasing, D to E is concave down, so D to E is decreasing and concave down. It's like that Taco Bell and Pizza Hut song. I don't know. I hope this helps. Thanks for watching. You are given the function j of x equals negative 8x to the 8th plus 5x to the 4th minus 4x squared. What is the end behavior of function j in limit notation? Well, in this case, the limit notation looks a little weird. Didn't mean to do that. Looks a little weird because, I created this using ChatGPT. And the way that they do it is instead of writing out the limit as x approaches infinity, they have it like on the bottom right corner here. It's all good. It doesn't really matter. What matters is we need to find the limit notation of something like this. Now, this produces a graph. This is also a non-calculator section, so I'm not allowed to graph this. And if you're like, what the heck does this graph look like? Whenever you're wondering what a graph looks like, this is what you do. You take a look at the leading term. Okay, the leading term is the term with the greatest degree attached to a variable, and that would be u. You're x to the 8th. You are an even exponent, not an even function, although this is, but it's an even exponent. Now, when it's an even exponent, the graph is either going to look like this or look like this. Okay, and of course these, little hoops and whatever are dependent on that number there, but I really don't care about what's going on the inside. It's the outside, which is the opposite of what we were told as children, that it's the inside that counts. Not for this problem, friends. We care about the outside. Now, the other thing that we need to look at is not the 8. I don't care about this 8 right here. I care about that negative. Any even function that has a positive leading term is going to go up as it moves to the left and up as it moves to the right. Well, if it's a negative leading term, it's going to look like U, which means as I move to the left, as the limit approaches negative infinity, we are also going downward, which means it's going towards negative infinity. And in this case, as I move to the right side without bound, or as the x values increase, or as x approaches infinity, we are also moving downward, which means we're also approaching negative infinity. So the limit as x approaches negative infinity of j of x, and the limit as x approaches positive of j of x, infinity of j of x, is also going to be negative infinity. So we need the ones with those negative infinities, and there you are, it's A. If this was an odd problem, then it would be like that or that, depending on, if you're positive or negative. But that's not what we have. That's not at all what we have. Oh, I kind of trailed off there with my grammar at the end. Either way, I hope this helps. Thanks for watching. Let T and V, something I watch too much of, be positive constants. Which of the following is equivalent to 3 log base 3 of T plus log base 3 of V minus 4 log base 3 of V? Well, whenever you have logs that are being added to each other, or ln's, because ln, by the way, if you forgot, happens to be log base e, it follows the same exact rules. If you have logs or ln's being added together and all of the bases are the same, you can combine them. And the way you combine them is if they're being added to each other, you multiply the insides, and if they're being subtracted, you divide the insides. But oh wait! The first thing you always need to do when you decide to combine logs is you have to notice if there's a coefficient in front of any of them. You have a coefficient and you have a coefficient. Whenever you have a coefficient, a number living in front of a log, the first thing that you always do is turn that 3 and turn that 4 into an exponent. So I would rewrite this as log base 3 of t to the third power. Move that t up here. You don't change because your coefficient is invisible 1, and I don't need to put invisible 1 as a power. That would be silly pants. That 4 becomes v to the fourth. So log base 3 of v to the fourth. Now, if you're wondering, oh, couldn't I have done negative 4 and then move that v downstairs? Sure. But that's not what I did. So I don't know. What do you want me to do? Now, the first thing I'm going to do is I'm going to move left to right, and I'm going to combine these guys through multiplication of the insides. When you add two logs of the same base, you multiply the insides. So log base 3 of t cubed regular v close parentheses. And then the minus log base 3 of v to the fourth comes along for the ride. When we subtract logs of the same base, we divide the first guy divided by the second guy. So you become log base 3 of t cubed v over v to the fourth. And if you're looking at these options and you don't see that as an option, that's because you didn't simplify the fraction, you rascal. I have a v in the numerator and 4 v's in the denominator. Don't you get rid of a v from each? You do. And you get log base 3 of t cubed over v cubed. And that would be u. Lots of threes. Lots of threes. Kind of like what Steph Curry does on the court. Hope this helps. The polynomial function q is given by q of x equals x plus 2 in parentheses times x squared minus 4x minus 20 in parentheses. Which of the following describes the zeros of q? Okay, well, what I would do is, I know zeros are when these guys cross the x-axis. So, like, a 0 would be -2 because you would set that equal to 0. If I were to set this equal to 0, minus 4x minus 20, set that equal to 0, I would get, I don't know, I'd have to factor that out. So two numbers that add up to -4 and multiply out to -20 are, wait a minute. There are no two numbers that multiply out to -20 and add up to -4. I can't factor this. Ugh. Well, that's frustrating. That is very frustrating. So I guess what I have to do is I have to go and use my dear friend, the quadratic formula. X equals -b plus or minus square root b squared minus 4ac all over 2a. I sang it and I wrote it at the same time. My a is invisible 1. My b is -4. My c is -20. So x equals -4, because b is -4, plus or minus a big square root of b squared, so in parentheses -4 squared, minus 4 times invisible 1 times -20 all over 2a. 2 times 1. All right, so let me see what I can simplify here. I can simplify -4 to +4, check. Plus or minus the big square root. I can simplify -4 squared into +16. -4 times 1 times -20 is going to be plus 80 all over 2. Okay, x is going to equal 4 plus or minus 96 over 2. I don't know what the square root of 96 is, so how am I supposed to do this without a calculator? Oh, wait a minute. I don't have to. It's just asking me how many answers I would get. Oh, okay. Well, this is going to be just, 4 plus 9 point something over 2, and 4 minus 9 point something, so I just get two ugly numbers. But what I would get is two ugly real numbers. So my pretty number up here was -2. My other option would be two ugly real numbers, so that's three distinct real numbers. Now, if you're like, well, duh, of course I'm going to get three answers. Let's be careful. Let's be careful. Let's go off over here and imagine a world where underneath the square root, we actually got a negative number. If that was the case, if you get the square root of a negative number, that's not a real number. That's imaginary. So you would have, in that fake case, two imaginary numbers. So if this was like, I don't know, minus 80, you would have 16 minus 80, which is a negative number. The square root of a negative number is not real. So that gives you two imaginary numbers, or two non-real zeros. So in that case, we would have selected D. But that didn't happen here. We got B. Life is good. We're done. Hope this helps. In the xy plane, the graph of a rational function f has a vertical asymptote at x equals 3, which of the following could be the expression for f of x. Now, if a vertical asymptote lives at x equals 3, that means there must be an x minus 3 living somewhere in the denominator and not an x minus 3 living somewhere in the numerator. Okay, if there was a x minus 3 living in the numerator like this guy, that creates a hole. So I don't want you, no. If I have, let me see, x minus 3, you're x plus 3. Oh, you're the opposite of what I want, so not you. You're x plus 3, you're x minus 12. And if you're like, yeah, but there's two x minus 3s up there, does that count? No, it's got to be in the denominator, silly, like that guy right there. Notice you have an x minus 3 in the denominator, an x plus 3, and who cares about these guys? That's all that really matters. And the reason why you want an x minus 3 in the denominator is if this were to equal 0, you would add 3 to both sides to get x equals 3, which is this guy right there. Now, why would we want the denominator to equal 0? Well, a vertical asymptote exists at a place that makes the function undefined, and it's undefined when the denominator equals 0. So I gave you a little bonus for this problem. But yeah, pretty simple. That's how you do it. Hope this helps. Let f be a sinusoidal function. The graph of y equals f of x is given in the xy plane. So yeah, you look pretty sinusoidal to me with all the waves and even more waves. What is the period of f? Now, the period of a sinusoidal function is going to be like the x value or the x distance that it takes for a sinusoidal function to complete an entire cycle. Okay, so, if this was like 5 and that was like 7, it looks like it takes 2 units to complete a cycle. Now, what I like to do with these, when the numbers aren't as nice or maybe it's not as clear, is I like to either start at 0 or pick a spot that's obvious. And in this case, a spot that's obvious happens to be at 0. So the very tippy top, or the maximum of this sinusoidal function, happens at 0. Okay, so we go down and we go up and we're at the very top again. So it starts repeating its process right around here. Down and up, repeat, down and up, repeat. So it starts at 0 and makes its way to whatever this guy is. Well, you're 1. So halfway in between 0 and 1 is, let me get my calculator, 1/2. So it takes 0 to 1/2 or 0.5 to get an entire cycle in. So there you have it. Now, don't confuse this with frequency. Frequency and period are different. This is the period, and that, again, is the x distance it takes to complete a cycle, and we just have half a unit here for it to do that. Hope this helps. Observe the graph y equals f of x, which of the following represents the transformation for the function g of x equals f of x plus 4 minus 1. So it looks like we have this weird half oval looking thing that happens between -1 and 3, and then it kind of starts at 2 and is almost a unit tall, but not completely a unit tall. So we kind of have it boxed in, between -1 to 3 and 2 to 3. Okay. And then we're given this guy f of x plus 4 in parentheses minus 1. Whenever you have a number being added or subtracted inside the same parentheses as x, you are looking at a horizontal shift. Okay. Now, a lot of teachers would say you move left or you move right, and that's all good and great, and that will help you understand this. But when you add 4, it's opposite of what you expect. You would expect that adding 4 has you go right 4 units, but that's not true. Whenever you see f of x minus something, it's that minus something that tells you whether you move left or right. So since this is a positive 4, you actually move left 4. This is worded as a horizontal shift of -4 because it would be written as x minus -4, x plus 4. And if you're looking at that and thinking point slope thoughts, you're thinking the right thing. So we're going to take this guy and we're going to move this to the left 4. I know I'm not done, but we're going to move this to the left 4. So 1, 2, 3, 4 has it ending up to the left right there. 1, 2, 3, 4 has it ending to the right somewhere over there. Now, when you subtract a number outside of the parentheses, and, it's just kind of some random number floating around, that is a vertical shift. This is normal. So -1 means down 1 in this case. We would word this in AP Precalculus as a vertical shift of -1. So I'm just going to take something that is left 4, and then you take that and just move it down 1. So it's going to appear as a semicircle somewhere around here, semi-oval or whatever that is. So stuff that happens between positive 1 and 2 now on the y-axis, and -5 and -1 on the x-axis, and B looks like the guy to do that. Okay, if you see numbers multiplied to f of x, that has to do with shrink and compression and all that stuff, or dilation. Numbers multiplied to x kind of changes stuff like that too, but we're not dealing with any of that. We're just dealing with horizontal shift and vertical shift. That's the end of that. Hope this helps. Thanks for watching. The exponential function f is defined by f of x equals a times b to the x, where a and b are positive constants. The table right there gives the values of f of x at selected values of x, which of the following statements are true. So they want to talk about exponential growth, they want to talk about exponential decay, blah, 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 blah. Since everything here is positive, right, exponential growth looks like this if you want to graph it out. Exponential decay would look like this if you wanted to graph it out. So like, let's say that you had zero clue what you were doing. At the very least, you have a 50-50 shot if you were to notice that, hey, these numbers are getting smaller, which means it would be exponential decay. Now, what we're doing is, yeah, these numbers are getting smaller. And it looks like what we're doing to get from 10 to 7.5 is you multiply by 3/4. And I'm assuming that's multiplying by 3/4 again. I don't know. The math is kind of wonky, but that's going to happen again. That's going to happen again. That's what you do when you have an exponential function. No, it's an exponential function. As long as these guys go up by the same number, that's equal length input values, intervals, these guys multiply by the same number. So we are exponential decay because we're multiplying by 3/4. Now, what that gives us is a b. See, whatever you're multiplying over here is basically my b, which is pretty much my base. A just changes the number, like makes it, like if I were to make a 4, this would become 40, and then this would still, that would be 30, and then that would still go multiply by 1/3 or 3/4 to move my way down. So b, in this case, is 3/4. So I know, again, this is exponential decay, which gets rid of u and gets rid of u. Now, why? A is positive. Well, we know A is positive because it says here that A is positive, so that's kind of a useless thing. But in this case, B is not greater than 1. A B greater than 1 would represent exponential growth, which is not what we have. So C is just a false statement to begin with. B is true because my B is 3/4, and by definition, exponential decay has a B in between 0 and 1, not including any of them. Okay, so A is going to be my guy. So by definition, again, A is whatever it is, it's got to be positive. But if B is greater than 1, you're looking at exponential growth. And if B is in between 0 and 1, you're looking at exponential decay. Like I said, this guy right here is just a false statement. Just like D would be a false statement because, if it's between 0 and 1, it's not exponential growth. So you're just a bunch of lies. Just a bunch of lies. And we don't like lies, do we? We don't. Thanks for watching. Hope this helps. Consider the functions f of x equals x squared minus 5 and g of x equals x over x minus 3. Which of the following is an expression for f of g of x? We have ourselves a composite function where g of x is going to live inside of f. So this is how I like to do composite functions. Whatever the guy is on the outside, I like to start writing that out first. So f of g of x, and let me get my colors, f of g of x is going to have me start out with f, okay? Now, I'm going to write out every part of f, but what I'm going to do is for every x in f, I'm going to leave a blank parentheses there. Because when you have f of whatever, you replace every x in f of x with that whatever. And it just so happens that my whatever is this ugly looking x over x minus 3. And x over x minus 3 is g of x. So I'm going to replace that with x over x minus 3. Now, doing a little bit of math, and it looks like I don't have to do too much math. I don't know. We'll see. We have x over x minus 3 times x over x minus 3. That basically means x times x, which is x squared, and x minus 3, which is x minus 3 squared, minus 5. And it looks like in this case, that's all I have to do and I end up with C. Now, if for some reason you were to take this like a step or two further, and if you're happy with this, end the video, you're done. But if for some reason you are given an option where you have to multiply this out and maybe even combine that, let's just do that for funsies. X squared is still x squared. X minus 3 squared is actually a perfect square trinomial. That's a FOIL problem. And if you need to take this extra step and write out x minus 3 times x minus 3, that's not the end of the world. We'll leave that minus 5 out there on the outside. I'll deal with you in a moment. Okay. Now, x squared upstairs in the numerator is still x squared. X times x is x squared. Minus 3x minus 3x is minus 6x, and then you become plus 9. Now, if I have to combine that minus 5 with this fraction, like let's just say like the option kind of looked like this, but you were required to do a little bit more, then what I would do is I would multiply that negative 5 to u in the numerator and the denominator. So u would become minus 5, x squared minus 6x plus 9, over x squared minus 6x plus 9. Why am I doing that? So I can combine fractions. So what I'm going to do is now I have x squared minus 6x plus 9 in the denominator. You are negative 5. Let's not forget that. You are negative 5. So you become, and by the way, this is me combining fractions and distributing at the same time. So x squared minus 5x squared. Negative 5 times negative 6x is going to be positive 30x. And negative 5 times negative 9, positive 9 rather, is going to be negative 45. Okay, and the only thing that we have to combine up here is that, which becomes negative 4x squared plus 30x doesn't combine with anything, minus 45 doesn't combine with anything, and you still have x squared minus 6x plus 9. So we're going to leave this like that. Okay, I'm not going to scratch anything out. I'm not going to cancel anything out. That's my guy. So, if you did the problem and you ended here and you felt like that's just too easy, maybe it's supposed to look like that. Well, no, it doesn't. We did everything right. It just so happens that our answer is a little bit friendlier than expected. But just in case the answer is not as friendly, we just did the work anyway. And you know what? It was fun. And I pray that you watched the whole thing. And if you did, I love you. But yeah, there it is. Hope this helps. The table shows values for a function f at selected values of x. So negative 2, negative 1, 0, 1, 2, 9, 4, 1, 0, 1. Ooh, it's not linear. And it looks like that's what we're supposed to do. I think I gave that away. Which of the following claim and explanation statements best fit these data? Well, it's not linear. And the reason why I know it's not linear is it went from 9 to 4 to 1 to 0 to 1, which means, if I repeat 1 here, it's not a straight line. But what you're supposed to do is you're supposed to go to your graph and you're supposed to find the rate of change. The first round of you finding the rate of change would determine whether or not something is linear. For example, what I'm going to do is I'm going to find out that to get from 9 to 4, we subtract 5. And to get from 4 to 1, we subtract 3. And 1 to 0, we subtract 1. And 0 to 1, we add 1. So since the rate of change is not a constant number throughout, it is not linear. Okay, if all of these numbers were the same, it would be linear. That's not what happened here. It's not linear. So maybe it's quadratic. And it looks like that's going to be my only option, but we need to make sure we explain it well. Okay, if I were to do the same exact process again, I need to end up with the same number. To get from negative 5 to negative 3, you add 2. To get from negative 3 to negative 1, you add 2. To get from negative 1 to positive 1, you add 2. So since the quadratic, or the rate of change of the rate of change, is the same constant number, we have a quadratic. So again, that phrase that I just said is every time you do a round of these, you are doing a rate of change. So the rate of change of the rate of change is a constant number. So this is a quadratic function because the rate of change over consecutive equal length input value intervals is constant. Well, that's not what I said. I said rate of change twice. So f is best modeled by a quadratic function because the change in the average rates of change over consecutive equal length input value intervals is constant. So the change of the rates of change, so change of change, oh boy. So lots of words there. But D is quadratic, And it tells me change of a rate of change, which means quadratic. So if it was cubic, it would be change of the rate of change of the rate of change, and you look for change 3 times. Looking for change 3 times sounds like I need to vacuum out my car and I need to find money. And I look for change. Hope this helps. The function g is given by g of x equals 3 cos 2x. Ooh, which of the following is an equivalent form for g of x? So g of x equals all of these. So if you're like, what are we doing here? Well, cos 2x implies that we are dealing with a double angle formula. Now, sine and cosine and tangent and all the others have double angle formulas, and the sine double angle formula, sine of 2 alpha or 2 theta, or in this case 2x, is going to equal 2 sine x cos x. Now, I know that's not what we're dealing with. I just gave you a little bit of extra just in case you see something like that. What we're dealing with is cos 2x. And we're usually used to seeing 2 different versions of this. One version of cos 2x is cos squared x minus sine squared x. Or the other version that we could see, because sine squared x could be turned into something else, is 2 cos squared x minus 1. Now, it looks to me, since we're dealing with the cosine version, I don't see any sines anywhere, so we're not going to deal with you. Okay, so we're probably dealing with this version of the double angle formula. So if you're looking for 2 cos squared x minus 1, you're not thinking correctly, because I'm multiplying 3 to this guy. So if cos 2x is going to equal that, then 3 cos 2x is going to equal 3 times 2 cos squared x minus 1. Distribute that 3, and you get 6 cos squared x minus 3, which is, oh, so close. Not you, you're missing that. It's going to be B. And it's going to be A. Well, that stinks. I guess I created a problem with 2 answers. Oh, silly me. But that's all right. Bonus. Bonus. And we had fun doing it. Hope this helps. The function g of x has the property that for each time the x values triple, the g of x values increase by 1. Now, before I even look at graphs, I want to remind you of a little guy. Every time the x values triple, the y values go up by 1. So like an example of this could be like 1, 2, 3, 4. That's the x values going up by 1. This would be like 1, 3, 9, 27. Now, what we have here is we have our x values going up, and by going up, we multiply the same number every single time to move our way upward as this guy moves up by 1. This, my dear boys and girls and others, is logarithmic. When the x values explode while the y values just add the same number to move up every single time, you are dealing with a logarithmic function. With everything being positive and happy and stuff like that, which it appears to be, logarithmic functions look like this, okay? Which means you're not logarithmic. I mean, maybe you're negative logarithmic, but that's not what I'm dealing with, because negative logarithmic would imply things going down, and that's not what we have. This is going up. This is my values tripling. So B is going to be my answer. C is exponential growth. And D looks like it's cubic. Or Cupid. I'm leaving it. You can't stop me. I'm leaving it. D is Cupid because I love cubic functions. Hope this helps. A complex number is represented by a point in the complex plane. The complex number has the rectangular coordinates 2 root 3. Which of the following is one way to express the complex number using its polar coordinates? Well, this is how complex numbers work. You treat it like a regular old point, all right? And this would be like the real axis, and this would be the imaginary axis. So if I were to pretend that this is a point in the regular rectangular plane, you would go right 2, and then you would go up. Let me see, root 3 is like 1.7, so 2 times 1.7 is like 3.5-ish. So you would go up 3.5-ish, and you would end up somewhere up here somewhere. Little context for you. So now, though, I need to turn it into polar coordinates. Well, what polar coordinates do is it gives you an r, which basically stands for radius, but really what it means is the distance from 0 to the dot, and then theta, which is the angle created from the positive x-axis to the side that you are creating right here. So I need to find r. Well, that kind of seems like, well, if I know that this is like, 2 over and like, 3.4 up, why don't I just do the Pythagorean theorem? And to find theta, which would be this guy, why don't I kind of just do like, SOHCAHTOA type stuff, and I know what the adjacent is and I know what the opposite is, so let's use TOA. Well, I have news for you kids. That's exactly what we're going to do. I just wanted to give a little context beforehand. Now, we do what we're about to do because it looks like Pythagorean theorem. If I give you rectangular coordinates and you need to find r, you find r by taking the square root of whatever this is squared plus whatever that is. So we'll call you a, we'll call you b, so a squared plus b squared. Again, if you're thinking, wait a minute, the square root of a squared plus b squared, that's like the Pythagorean theorem, only that's r and not c. That's exactly what it is. You're absolutely right. If you're thinking that, good work. Good on you. But what's my a? We called a 2, so 2 squared. B is 2 root 3, so we'll 2 root 3 square. Okay, 2 squared is 4. 2 times 2 is 4. Okay, root 3 times root 3 is 3. So 4 times 3 is 12. Don't know why I put parentheses around that. But what we get is we get square root of 16, which is 4, baby. So what we have so far is we have an r of 4. What we don't have is theta. Now, again, what I showed you before, what we saw before is we basically put a dot right there. We knew that this was 2. We knew that this was 2 root 3. And my job is to find this angle right here. Well, if I was thinking SOHCAHTOA, I would think that the tangent of theta is going to equal the opposite over the adjacent. Or we could just write out that theta equals the inverse tangent of b over a. So have that guy memorized. Have you memorized? Have you memorized? That's going to equal the inverse tangent of what was b, 2 root 3 over 2, which simplifies to the inverse tangent of cross you out root 3, which is pi over 3. Took a second there. All right. So now what we do in order to write this out in complex form is written out as r cos theta plus I r sine theta. So we know r is 4. So r is 4 cos. We know theta is pi over 3. So pi over 3. Plus 4i, I did a little switcheroo there, sine pi over 3. Which looks like you. Tricky. If you looked at this, though, you might be able to notice that you kind of remind me of a 30, 60, 90 right triangle. Well, because it is. And if you notice that, that might make life a little bit easier. But, it's just a little fun stuff. Hope this helps. The figure shows a circle centered at the origin with an angle measure theta radians in standard position. So there you is. The terminal ray of the angle intersects the circle at point P. There you is. Q also lines on the circle. Hi, Q. The coordinate P, or the coordinates of P, are x and y. The coordinates of Q are x and negative y. Right? Which of the following is true about the cosine of theta? Well, whenever we have something where the unit circle is not giving you a radius of 1, we know that we have r cos theta, r sine theta. We're worried about cos theta. The x value is cos theta. So r cos theta equals the x value. Now, if I want to find out what cosine of theta is, dividing both sides by r tells me that cos theta is x over r. Now, what else do I know? Well, x is x. That doesn't help me. Ooh! That 2 means I go from the pole here, from the origin, all the way out to 2. That's a radius, which means r is 2. So I can write this guy as cos theta equals x over 2. Now that's what I have so far. Now clearly they want me to do a little bit more explaining, but let's see if we can figure this out. So cos theta equals x over 2, so let's, bookmark that for a second. Cos theta equals negative y over 2. No, that would kind of be like sine, but upside down. Cos theta equals y over 2. No, that would be regular sine. And cos theta equals y over 2. Well, that sure made life easy, didn't it? Now let's try to understand why, just for funsies, because it is the ratio of the horizontal displacement from P to the y-axis to the distance between the origin of P. So what that is saying is, since cosine is an x value, right? Cosine gives you that horizontal displacement. Horizontal displacement means how far am I going left to right? So if it gives me an x value, that means we care about horizontal displacement. So whatever x value this is going to give me that. Also, it's the ratio, which means the fraction of the horizontal displacement. So x is the horizontal displacement to the distance between the origin of P. And that's where 2 comes from. So it's the ratio of the horizontal displacement over the ratio, which is 2. So it all kind of connects. Sine would be the ratio of the vertical displacement. And so you would get something like sine of y over 2. But, that's not what we have here. We are dealing with cosine because that's what it asked for. Crazy problem. And if you're wondering, well, what's the point of all this Q stuff? I don't know. I didn't make the problem. Well, actually, I did make the problem, but we didn't have to worry about it because Q didn't matter. Hope this helps. The function f is given by f of x equals negative 2x squared plus 5x minus 1. The graph of which of the following functions is the image of the graph of f after a vertical dilation by a factor of negative 3? All right, so what a vertical dilation does is it takes a parabola, and this is a parabola. I actually have it upside down. It takes a parabola, and it makes it skinnier or wider depending on the number. Now, what negative 3 does is it makes it skinnier and also flips it upside down. Now, this is not to be confused with a vertical transformation, or translation rather, which moves it downward or moves it by a factor of negative 3. This is a vertical dilation. What you do with a vertical dilation is whatever function you have, you multiply that number to the entire function. So we would say that the image would be negative 3 times f of x. So what that means in our case is a negative 3 times f of x, which is negative 2x squared plus 5x minus 1. So you distribute negative 3, 6x squared, distributive negative 3, negative 15x, distribute negative 3, positive 3. 6x squared minus 15x plus 3 is our result. So that's good. That's awful close, but upside, it's backwards. It's everything but the opposite. I don't even know what the heck this is. This is a mess. I don't like it. And that is basically, I don't know what that is either. This would be a vertical translation, like I was saying. A vertical translation would be f of x not equals, I'm sorry, f of x minus 3. So basically all you would do is you would take your f of x and subtract 3 to get negative 4. That's what this is. They were hoping you would misread this. But it's going to be this guy right here, because it's the multiplicative transformation of f that results from multiplying each output value of f of x by negative 3. So that's what we did. Just be careful of the wording again. When I initially saw this, I was going to be like, oh, how easy. You just subtract 3. And that's not what it was. Unfortunately, that's not what it was. But at the end, it wasn't really that bad anyway. So hope this helps. You create a table of x, f of x, and g of x values. I read that very poorly. It's given that h of x is g of f of x. Oh, a composite function. Given the table, find h of 1. All right, so h of x. Let me get my colors. Equals g of f of x. Which means h of 1 is going to equal g of f of 1. So whenever we have a composite function, we always deal with the inside first, f of 1. That means I take my f column, which is u, I replace x with 1 and find out that 1 maps to 3. So f of 1 is 3. So h of 1 equals g of 3. G of 3 has me going to the g column and finding out what 3 is and saying g of 3 is 10. So h of 1 is 10. So h of 1 is 10. So there you have it. H of 1 is 10. Composite functions involving tables, pretty easy stuff if you know what you're doing. I mean, all of this is easy if you know what you're doing, but this one's not so bad at all. Hope this helps. The function f and g are defined by all real numbers such that g of x equals f of 3 times the quantity x minus 5, close, close. Which of the following sequences of transformations maps the graph of f to the graph of g in the same xy plane? All right, so it looks like I have a 3 being attached to the parentheses with an x minus 5. If you're doing this and watching these videos, you're probably already done units 1, 2, and 3. And so you might compare this to like a sinusoidal thing where you move left and you move down and you stretch things out and you have a period of whatever. This is very similar, but it's from unit 1. And from unit 1, we would label things as a times f of b of x minus c plus d. So it's very, very varies to the sinusoidal stuff. Okay, with the sinusoidal stuff, the a was amplitude. Okay, now what we have here is similar. Amplitude is kind of like height. It's half the height, but it's like height. What we have here is a vertical dilation. Okay, it's how things stretch or shrink vertically depending on the number. What we have for b is very similar to the frequency if this is sinusoidal. This is a horizontal dilation. And if you're like, how is that similar to the frequency? The frequency is kind of like, a stretch left to right. Well, just like frequency, the frequency doesn't give you what we're used to when doing sinusoidal functions, which is period. The b is counted as 1 over the factor. So just like the frequency is 2 pi over the period, the b is 1 over the factor that we're dealing with. So whatever number that we get in front of it, x, it's actually its reciprocal. So that's the horizontal dilation. What we have inside the parentheses is like the shift, but we call it the horizontal translation where you move left or right. Now, since the negative is already there, if we see something like x minus 5, that actually means you move right. You move positive 5 units. If the negative is positive here, it's opposite from what you're used to where you move left. Okay, so we'll keep that in mind because we have that in this problem. Now, D is like it always is. When you have some number being added or subtracted on the outside of all this stuff, you have a vertical translation. And, if it's up, it's up. And if it's down, it's down. Plus 3 means you move up 3. Down 3 means you move down 3. Now, what I have here is I have nothing in front of f. So, the a part that we have here means nothing. Okay, we have f of 3 of x, which means the b that we care about is 3, x minus c, so c is 5, and then we have no number being added or subtracted on the outside, so we don't have to worry about a vertical translation. The b is the horizontal dilation, but we write it out as its reciprocal. So what's going to happen is we're going to have a dilation by a factor of 1/3. So the horizontal dilation is actually 1/3, the opposite of what we're used to. This is minus 5, which means if it's x minus c and x minus 5, c is positive 5, which means we have a horizontal translation of positive 5. So we need the one that describes a horizontal dilation of 1/3 and a horizontal translation of 5. So horizontal dilation of 1/3, no. Horizontal dilation of 1/3, no. Horizontal dilation of 1/3, yeah. Horizontal translation of -5, no. We went positive 5. Horizontal dilation of 1/3, yup. Horizontal translation of 5, yup. You're the guy. So I think many people would look at this and probably get the right idea and maybe think that the dilation is 3. It's just you have to be careful, just like the sinusoidal stuff where it's frequency and period and it's all upside down and backwards. The same thing happens here. Okay? I don't like these problems, but what are you going to do? Got to do them anyway. Hope this helps. Which of the following could represent the graph below? So we have a sinusoidal function, obviously, and we have all of these graphs where there's similarities amongst all of them. Like, for example, for all of them, the amplitude is 2. Now, before we tarry any further, let's compare this to what a sinusoidal function looks like. Okay, you have a times either sine or cosine, so sine, cos, of b of x minus c, close it, plus d. A is the amplitude, amplitude. B is the frequency. Now the frequency is 2 pi over the period, or if it helps, the period is 2 pi over the frequency. Let's see if we have to deal with that. We'll wait a minute until we get there. C stands for the horizontal shift, also known as the phase shift. Now, it's opposite of what we're used to, okay? Where if this was something like x minus 3, you actually move to the right 3. It's a positive horizontal shift. D is your midline, also known as your vertical shift. Okay, now when I look at a thing like this, if we're given the graph and we're being asked to figure out multiple choice which is which, to me the easiest thing to do is figure out what the midline is. The midline is exactly what it sounds like. It's a line that cuts our graph in half. So it's a line that cuts our graph in half. So here, the midline, the D, is going to be y equals 1, or in this case, we'll just say 1. So we know that whatever we have is going to be blah, 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 plus 1, which eliminates u and eliminates u. Now, what I'm left with are two sine functions with an amplitude of 2. So we can see that the amplitude is 2 because it goes up 2 or down 2 from the midline, however you want to view it. We have a half for our frequency. Okay, so there's no use in us calculating that. That's not going to help us. And the only difference that I see here is that we have a 2 multiplied here. So that's different, and that shouldn't be there. We shouldn't have a 2 in front of x. So I'm going to kind of wait until the end to deal with that to see if that's something I really need to deal with. So I'm going to look at this and see if everything checks out. Amplitude of 2 checks out. Okay, we have the same 1/2, but just because that's a 2, maybe I should figure this out. If the frequency is 2 pi over the period, it's always easier for me to find out what the period is than to find out what the frequency is. So the period is 2 pi over the frequency. So the period is 2 pi over 1/2 according to this equation. So you multiply the top and the bottom by 2 to get rid of that 1/2 on the bottom, see it goes away, and you have a period of 4 pi. So in order for me to find the period, what I like to do is either take the tippy top or the very bottom and to find the distance, and that distance is going to be negative 2 pi to 2 pi 4 pi. Now, in order for this to work out, we would have to factor out a 2, which means bring out a 2, which changes that number. So B is not going to be my answer. Okay, but just to continue the problem, just to make sure we all feel comfortable, minus pi means we actually shift a positive pi, which means we take a sine function and we move it to the right pi. Okay, sine is supposed to start and look like this. Go that way. So if the midline is 1, and if I were supposed to start here and I move right pi and actually start here, I'm good. So that checks out. Okay, that checks out. And of course, last but not least, we started out by using the midline to eliminate these two. Midline is 1. We're good. So my answer is D. So I scribbled everywhere. But the idea is, you start with the midline. Sine or cosine might change the vertical or horizontal shift, rather. That 2 there threw everything off. But if I factored out the 2, that changes the frequency. But the frequency is right. Just a lot to see here, a lot to do with. But we did it. And I hope this helps. Let f be a rational function that is graphed on the xy plane. Consider x equals 2 and x equals 8. You got it. The polynomial in the numerator, all right, so got a fraction here, has a 0 of x equals 2. If there's a 0 of x equals 2, that means it has a factor of x minus 2 because it's always the opposite. Okay? It does not have a 0 of x equals 8. All right, so if there was, it would be x minus 8. The second sentence, or the third sentence? I don't know. The third sentence, fifth sentence, fourth sentence. The polynomial in the denominator has zeros at both x equals 2, all right, so x minus 2 again, and x equals 8, so x minus 8. The multiplicities of the zeros at x equals 2 in the numerator are equal. All right, well, so that's good. So I'm just not going to write anything out for these guys. Which of the following statements is true? So it's talking about holes and vertical asymptotes and stuff like that. So before I even look at the complete multiple choice thing, anytime you have the exact same factor in the numerator and the denominator, and the multiplicities are the same, which means the exponents that are attached to the parentheses are the same, you have a hole. Anytime you have a factor in the denominator that does not repeat in the numerator, you have a vertical asymptote. If we had something in the numerator that was not like anything in the denominator, we would have a 0, but we don't have any zeros in this problem. So we have a hole at x equals 2, and we have a vertical asymptote at x equals 8. So the graph has holes at both x equals 2 and 8? Nope. The graph of f has a vertical asymptote at 2 and 8? Nope. That's the hole at 8. That's the opposite of what we want. The graph of f has a hole of 2? Yup. And a vertical asymptote of 8? Yup. And the graph of f has vertical asymptotes at both, so nope. So pretty basic Unit 1 problem. Pretty easy. Lots of fun. Hope this helps. Consider the following table representing x and y values for this function 1, 2, 3, 4, 2, 1/2, and 1/4. Which of the following functions could be used to represent the data? So we have ourselves something that's linear, we have ourselves something that's quadratic, we have ourselves something that's exponential, we have ourselves something that's exponential. So let's do the linear first. The way you find out if something is linear is you see what you have to add to these guys and see if it's the same number. Find the rate of change. So to get from 2 to 1, you subtract 1. To get from 1 to 0.5, you subtract 0.5. To get from 1/2 to 1/4, you subtract 1/4. So these are not the same number. These are not linear. Now, the way you test to see if something is quadratic is you find the rate of change of the rate of change. See what you have to add to these numbers to get to the next number. So to get from -1 to -1/2, you add 1/2. And to get from 1/2 to -1/2 to -1/4, you add 1/4. So you're not quadratic either. So you must be exponential. So let me get rid of this, and let's do our exponential test. Now, exponential equations are in the form y equals a times b to the x. What I'm going to do is I'm going to see what I've multiplied to each number to get to the next number. If the numbers are the same, that ends up being my b, my base. So how do I get from 2 to 1? Take half of it. How do I get from 1 to a half? Take half of it. How do I get from a half to a quarter? Take half of it. So what that means in this case is that b is a half. So what I have is y equals something times a half to the x, which eliminates u. Now, if you're a little paranoid and wondering, well, where's that 4 coming from? Once you plug in a number, once you substitute in 1, you're going to get 1 half to the first power, right? Which is a half. Well, I'm supposed to get 2. So what do you multiply to a half to get to 2? 4. So 4 is basically that multiplier that you use to get the number that you need. So again, if I were to plug in 2, I would get 2 to the, or 1 half to the second power, which is a quarter. 4 times a quarter is 1, and then so on and so forth. So D is our guy. D makes sense. Exponential. Hope this helps. The polynomial function p is given by p of x equals ax to the fourth minus bx cubed plus 20, where a and b are non-zero real constants. Great. Each of the zeros has a multiplicity of 1. In the xy plane, an x-intercept of the graph of p is 20.00070. Oh, okay. And a 0 of p is this complex number right here. So this problem looks much more frustrating than it has to be. So basically, this is what happens. We are going to have 4 answers. How do I know we're going to have 4 zeros, 4 answers? Well, because that's to the 4th power. This is a real number. This is imaginary. So if you're going to have any amount of imaginary numbers, it's got to be an even amount of imaginary answers. So we have 2 imaginary answers, which means if we have 2 imaginary answers, we could have 4 if we weren't given this information. But since we were given this information, this is telling us, look, here is 1 real answer. Here's 1 imaginary answer. There's 4 total answers. What do you have? Well, you must have an even number of imaginary, which means we're going to have an even number of real since we know we have 1. We can't say 1 real, 3 imaginary. You can't do that. Now, here's the thing. Without doing the math, I don't know what the other real number is. But if I'm given the imaginary number, the other number is going to be its conjugate. Always, always, always. To find a conjugate, you just take the number in front of the imaginary I and flip the sign. So I know I have an answer of u, and I know I have an answer of u plus 0.903i. So what I know is I have 2 imaginaries, 2 reals. 1 imaginary is this. The other imaginary is that. 1 real is this. I don't know the other real. The graph of p has 4 x-intercepts. Well, no, because you're imaginary, which means you never cross the x-intercept. Bye. Negative 0.601 plus 0.903i is a 0 of p. Yeesh. The equation of p of x equals 0 has 4 real solutions. No, there's 2 real solutions, 2 imaginary. And the graph of p is tangent to the, who cares? No, we're not worried about tangents. We're not going to worry about tangents and sinusoidal stuff. This has no indication that we're going to deal with any tangents, anything like that. Okay, so yeah, that's fun stuff. That's fun stuff. The answer is B. Hope this helps. Consider the functions h and k, ooh, Harry Callis, rest in peace, given by h of x equals ln of x plus 2 plus ln of x plus 5, and k of x equals ln of x plus 5. In the xy plane, what are all the x coordinates of the points of intersection of the graphs of h and k? This is just fancy talk for set these guys equal to each other. So what I'm going to have is I have an ln of x plus 2 plus ln of x plus 5 equals ln of x plus 5. Now, I guess what I could do, I could approach this 2 different ways, okay? I'm going to approach this in the unnecessary complicated way. but it's good because it's going to be helpful for both. Complicated way, okay? Now, keep in mind, ln is the same thing as log base e, so it follows all the log rules. So you can combine these two, since this is adding, by multiplying the inside. So what we have is ln of x plus 2, x plus 5, parentheses, equals ln of x plus 5. If you have an ln on the left and a single ln on the right, if you just take e of both sides, all the ln's cancel out, and now you're left with x plus 2, x plus 5 equals x plus 5. So this is a FOIL problem. FOIL that out. X squared plus 5x plus 2x plus 10 equals x plus 5. X squared plus 7x plus 10 equals x plus 5. Subtract x and subtract 5. X squared plus 6x plus 5 equals 0. Use the zero product property to factor that out, and you'll get x plus 1, x plus 5 equals 0. What that means is your possible zeros using the zero product property is going to be -1 and -5. Now, before we come up here and circle C, ln is tricky because you're never allowed to have an ln of 0, and you're never allowed to have an ln of a negative number. If I were to take -5 and go up here and plug that into the very first ln that I see, I would get ln of -5 plus 2 is -3. That's no good. You can't have an ln of -3. You can't have an ln of negative anything or 0 for that matter. So -5 is no good. The answer is B. Now, that was the complicated way, the way that you would do this 90% of the time. Now, the other 10% of the time is uncomplicated because I noticed something right off the bat. And if you're wondering, why couldn't you have done this in the first place? Listen, this is YouTube. The more time that I use doing these problems, the more money I get. If you notice right away that you have ln on the left and ln on the right, they just cancel each other out because you can subtract ln of x plus 5 from both sides. So you have ln of x plus 2 equals nothing. So you take the e to the of both sides. That makes that ln go away, leaving you with x plus 2. Anything to the 0th is 1. Subtract 2 from both sides. 1 minus 2 is -1, just like we got right here. And you don't have to worry about the -5 ruining everything. You're allowed to plug in -1. You're allowed to plug in -1. All is well. The reason why this ended up weird is because this problem that I created, I wasn't thinking, and I made ln of x plus 5 twice. But you know what? This gave us two different ways of looking at it, and boy, did I have fun. Hope this helps. For 0 is less than or equal to theta, which is also less than 2 pi, which values of theta make 3 sine theta plus 2 sine squared theta equals -1 true? Whenever I see this, I just make believe in my head that sine theta is A. Let's just pretend that sine theta is A. You'll see. So I would write down something like, 3a plus 2a, that's sine squared theta, so a squared equals -1. If I add 1 to both sides, and rearrange things like so, you should be able to look at that and say, by golly, that is a factorable problem. I could probably factor that out to 2a plus 1, and regular a plus 1 equals 0. And then, of course, you double check to make sure it works, and it works. You really have no other options. I mean, the quadratic formula could be used, but who the heck wants to do that? So what you're left with here is you would say 2a plus 1 equals 0. Subtract 1, divide by 2, you get -1/2 is equal to a. That's cool. Also, subtract 1, and you get a equals -1. That's also cool. Now, before you go over here and go like, oh, what the heck? Where's negative a half or where's negative one? Buddy, I didn't start out with A. I started out with signs. So remember, we pretended that A is negative a half, or we pretended that A is sine squared. So that means sine theta, not squared, boy, oh boy. Sine theta equals negative a half, and sine theta equals negative one. Okay, so let me scooch that over here and just rewrite them just for, because I have the space. Sine theta equals negative a half. Oh boy, I left some space there. I don't know why I would do that. Sine theta. I hope I don't do that again. Oops, I did. Now, why would I do such a silly little thing, leaving all that space? Well, if I want to get theta all by itself, which is what I'm doing, I'm solving for the values of theta, I'm going to inverse sine both sides. What that does by inverse signing both sides is that crosses u out. So now I have theta equals the inverse sine of negative a half. Now, the inverse sine of negative a half, let's think of what sine is. Okay, sine is a y value, so all of that stuff happens underneath here, underneath the x-axis. So if we're thinking unit circle thoughts, and you have a unit circle right here, when would y equal a half? Well, right here and right here, the dot's closest to the x-axis. That's when y would equal a half. So what you are is you are 7 pi over 6, and you are 11 pi over 6. So my two thetas that give me negative a half are going to be 7 pi over 6 and 11 pi over 6. Now that's one of these. Now I have to do the other. So I'm going to inverse sine again. Inverse sine again. So I have all that space. That crosses out. So theta equals the inverse sine of negative 1. Again, sine is a y value. On the unit circle, when is the y value negative 1? Well, just down here. Okay, the y value is 0, the y value is 1, the y value is 0, the y value is negative 1. That's 3 pi over 2. So theta is also going to be 3 pi over 2. So my options are 7 pi over 6, 11 pi over 6, 3 pi over 2, not necessarily in that order, but that gives B as our answer. Fun stuff. I like solving trig functions. It makes you think. Hope this helps. The graph shows the polar equation f of theta equals r equals 3 sine 2 theta. I don't really need to worry about the f of theta part. It's just fluff. It's graphed on the interval 0, 2 pi, as most polar functions are. A student, U, wants to trace over the portion represented by the interval pi over 2 pi. Where in the polar coordinate system would this portion of f of theta or r be found? So I'm talking about quadrants here. Now, if you're ever trying to view a polar graph and you're having a hard time viewing it, don't view it as the polar graph. View it as its regular trig function. Okay? So if we have a regular trig function, 3 sine 2x, for example, we would go up to 3, we know that. We would go down to negative 3, we know that. The frequency is 2. If the frequency is 2, that makes the period 2 pi over the frequency, or 2 pi over 2, which makes the period pi. And we have a sine function. So what's going to happen is we're going to, and let me label this pi, let me label this 2 pi. So you would be, what is this? 3 pi over 2. You would be pi over 2. And what we're going to care about is this area right here. Okay, so making a very rough drawing of what 3 sine 2x would look like. It's a sine, so it starts up here, it peaks out, it bottoms out here, it bottoms out, and starts over again. Peaks out up here, hits the x-axis, bottoms out here, and starts over again. So one more time, it's going to go up and down. Now, this is the part that really matters. Pi over 2 pi. So let me choose a different color. Bottoms out to -3 and then comes back up again. Now, the rest of it doesn't really matter that much, but you know what? I'm going to draw it out because I'm committed. All right. So this is what we care about. What we care about is this red area down here. What this red area down here suggests is that at pi over 2, we are at 0 at pi over 2. Then from our way to pi over 2, we are in negative land. Okay, so we go towards -3 to pi, and then back up again to pi. So let me see. Let me pick some numbers that I could use. So like at pi over 2, which is right here, we're at 0. As we move over from pi over 2 to pi this way, we're not coming out this way. We're in negative land. So we're actually going out this way. Okay. So we go out to 3, then come back to 0. So from pi over 2 to pi, we go out to -3, which is 3 in the opposite direction, and go back to 0, and then we're done. Well, that's what I did. I went out to 3 in opposite land. +3 would be out here, so we're going out to -3 in opposite land and back to 0, and then we're done. So this green line that I drew here, I'm finished. So all I have to worry about is just quadrant 4. And so that's my answer. So these problems are kind of weird. Again, you know, it's all a matter of preference how you do these. I like to view these as regular old rectangular trigonometric functions, and I graph them as such, and I try to make a pretty picture to make this a pretty picture, and I think it worked. So, helped for me. Hope this helps for you. Ah, yes, the old Ferris wheel problem. It has a radius of 30 meters and rotates completely every 100 seconds. The bottom of the wheel is located 2 meters above the ground. Create a sinusoidal equation, h of t, to represent the height h in meters of a passenger as a function of time t in seconds, assuming the passenger boards at its lowest point. All right, so what do I know? I know I have a Ferris wheel. There it is. I know that I have a radius of 30. Now, fun fact, whenever you're dealing with the sinusoidal function and the example that they give you is a circle, the radius is always the amplitude. Okay, so that's number one that I know. I know if I were to graph this out, I know my amplitude is 30. So I like to make a rough graph. Not that it's necessary for this, but I always like to make a rough one anyway. So I know that the amplitude is 30. Great. It rotates completely every 100 seconds. That, boys and girls, is the period. So over here, I'm going to have 100 seconds. The bottom of the wheel is located at 2 meters. Okay. 30 meters is the radius. So at the very middle of everything, if this is 2, at the very middle of everything, we're at 32 because, you know, 2 plus 30 is 32. And at the very top of everything, we're at 62 because 32 plus 30 is 62. So 2, 32, 62. We start at the bottom, just like Drake, and then we make our way up and come back down with that perfect picture right there. Now, what do we know? Well, again, we know that the amplitude is 30. So if I were to start building a trig function, I know it's going to be 30 times, I don't know, sine, cosine, we'll figure it out. Okay. The period is 100 seconds. So when I'm building an equation, I don't really care about the period. I care about the frequency. And the frequency is 2 pi over the period. So 2 pi over 100 simplifies out to pi over 50. So what I have so far is pi over 50. Now my options start to slim down a little bit. You're not pi over 50. And you're not pi over 50. You're upside down. So it's not A or B. Okay. Now, I'm looking at this, and it's like, one of these is wrong. And you're clearly the one that's wrong. But why is it C? And why is it negative? Well, if we look at this, if you're thinking it's cosine, technically you're wrong. Cosine starts up at 1. If you make cosine negative, you flip this over the x-axis. So a negative cos graph looks like this, which is what we have here. So we have a negative cosine graph. Okay, so I could just get rid of all this. That's just sloppy. Negative cosine, so negative 30 cosine. If I'm starting at the bottom and I know it's negative cosine, I have no horizontal shift, so I'm not going to have anything added or subtracted to t. So that remains pi over 50t. And if you're wondering, well, wait, where do these numbers come from? 32 is the midline. You always add the midline to the very end here. So my equation is h of t equals negative 30, because again, it's negative cosine. It starts at the bottom. Why is it 30? Because the amplitude's 30. Pi over 50. Why is it pi over 50? Well, the period was 100, and the frequency can be found by doing 2 pi over 100, pi over 50. T is attached. No horizontal shift because we're starting with negative cosine, and none of these display horizontal shifts, so I'm not going to try to force anything. And why is that plus 32? Well, you always add the midline on the outside of the function. So that's our guy, and that's our guy. I hope this helps. Consider the graph of the polar function r equals f of theta, where f of theta equals 2 plus 3 cos theta in the polar coordinate system for 0 between, or theta between 0 and 2 pi. Which of the following statements is true about the distance between the point with the polar coordinate f of theta, and the origin? All right, I did a problem like this in a previous part of the test where I don't like to look at these and try to draw this out. Like, I know this is going to be like one of those heart-looking guys. It's going to look something like this, or maybe it looks something like this. I don't know. It's going to look something like that, but I don't, that bothers me. I'm not good at that. So what I'd rather do is view this from a regular rectangular coordinate system. Okay, I have an amplitude of 3 and I have a midline of 2. So if I were to put a midline at 2, I know this is cosine. It's going to start way up here at 5, come back down, bottom out at 1, and repeat. So bottom down at -1, I mean. Now, why -1? Well, if this is 2 and the amplitude's 3, that means the very tippy top is 2 plus 3, and the very bottom is 2 minus 3. So it peaks out at 5, bottoms out at -1, repeats at 2 pi because there's no frequency, or rather the frequency is invisible 1. So it's asking me which of the following statements is true about the distance between the point with our polar coordinate f of theta, I think that's backwards, I don't know, whatever, and the origin. Well, the distance is increased. Oh, okay. So they want us to look at all of these options. They want us to look at all of these options and see which one is true. Okay, so basically I'm just going to, look at my points and see what's going on. So, I might mark up this graph that I have and, make it different. I don't know. We'll see. You are pi over 2. Okay, because it crosses the midline there. You bottom out, so you are pi. You cross the midline there, so you're 3 pi over 2, and you're 2 pi. A is asking me pi over 3, which is a little bit less than pi over 2. Remember, if you're thinking unit circle thoughts, pi over 3 is like a third of the way to pi, so you're like right here. And pi over 2 is right here. You are positive and increasing? Nope, you're positive and decreasing. So A is not correct because true, but not true. Okay, so let's choose another one. Between pi, so here's pi down here, and 3 pi over 2, so let's choose a different color dot and say 3 pi over 2. Between pi and 3 pi over 2, it's negative and increasing. Well, it's increasing, but it's not negative. It's negative right here, but then all of a sudden it becomes positive. So this is true, this is not. Let's try C. The distance between, pi over 3 again, so let's move you back to right around here somewhere. And pi over a half, very close to it. The distance is decreasing, that's true, because it's positive and decreasing on the interval. Well, yeah, there we go. We finally have it. So this is going down, and it's above the x-axis, so my guy is C. Now, why is D incorrect? The distance is decreasing from pi to 3 pi over 2. Well, it's not. It's increasing. So that's just immediately wrong, which makes the whole thing wrong. But there you go. The answer is C. Fun. Hope this helps. Here we are to the GOAT's ultimate practice test, and we finally have a calculator section. The worst and most annoying part about the calculator section of any AP exam is you probably don't need a calculator for most of them. For example, this one, you don't need a calculator for. So I'm not going to pull out the calculator. Why do they pull it on the calculator section? I have no idea. I'm not the Lord of AP. But a turtle is walking away from her home at a constant pace for 5 minutes. The turtle then stops for a short time to rest. After resting, the turtle spots food and moves at a rate 2 times faster than before, reaching her destination at 10 minutes. So without looking at this, you have a turtle walking slowly. At 5 minutes, it stops, and then it doesn't give us a specific time, but what it says, it goes 2 times faster. So you're going to try to make a line that's 2 times steeper, and then all of a sudden you hit 10. So which one of these has a regular line going to 5, stops for a little bit of time, and then has a double-looking steepness line, and then stops at 10? You look like you are going to 5, stops, but this line is the same as that line. That slope is the same as that slope, or at least it looks like it. Like if I were to take that line right there and compare it, yeah, they're the same. So you are not it close, but you are not it. You are going at a regular pace, stops, and that looks like it's double. That looks like it's double. I mean, you go from 0 to 5 in like 5 minutes. So, like 1 foot per second, 1 mile per hour, whatever it is. Okay, then all of a sudden you go from like 7 to 11 or whatever pretty quickly. So you have promise. So I'm going to hold on to you for a second. C has me going really fast, stopping at 5, and then slowing down because this slope is obviously not as steep as that slope. And then D kind of looks like the same thing, but I'm just going to ignore D because D has me saying that I stop at like 3 minutes or whatever, and this has me stopping at 5 minutes. So D's no good. So yeah, B is the correct answer for this guy. Again, where was the calculator for this problem? Nowhere. Nowhere to be seen. But, that's the way these AP tests go sometimes. They say you should use a calculator or can use a calculator, but you don't need to use the calculator. So hope this helps. In a certain simulation, the population of a virus-infected cells colony, sounds like fun, can be modeled using a geometric sequence, where the first day of the simulation is day 1. That's usually the case. The population on day 4 was 8,000, all right, and the population on day 8 was 72,000 virus-infected cells. What was the population of the colony on day 6 based on the simulation? Well, we have ourselves a calculator problem, and if you're wondering, how can I do this problem? There's no geometric sequence thing on my calculator. You're right, there isn't, but there's a little guy called expreg. And if you're like, what's that? That's called exponential regression. And what exponential regression does is gives you an exponential function. And if you're thinking, yeah, okay, great, but it says geometric sequence. Buddy, a geometric sequence is an exponential function. They're the same thing. It's just usually a geometric sequence deals with like a term 1, term 2, term 3. And with exponential regression, you're allowed to use like zeros and stuff like that, negatives. Where that wouldn't really make sense with a geometric sequence. They're still the same thing. So what we're going to do is we're going to run to our calculator. We're going to plug everything in. We're going to actually plug in 1, 8,000 and 8, 72,000, hit exponential regression, get an equation, and then see what happens when we plug in 6. Let's do it. All right, so if we're going to do any type of regression, exponential, linear, whatever, the first thing you're going to do is you're going to hit stat and then hit edit. Okay, so the 2 points that I had were 4, 8,000 and 8, 72,000. So 4 and 8 are going into my L1, my list 1, and 4 matched up with 8,000, so let's type that in, and 8 matched up with 72,000, so let's type that in. Let's go back to stat. Let's go back to calc. And what we want is exponential regression, which is way down here at 0, exponential regression. You're going to hit enter a bunch of times. Now, here's the thing. I'm going to use this equation to answer a future equation. So what I want to do is I want to store this so that when I hit y equals, it's going to be there. So you go to store regression equation, go to vars, go to y vars, hit function, hit y sub 1, and what that means is that's the equation that I come up with is going to store it in y sub 1. So we hit calculate, lots of 8s, 1 point whatever. I don't want to have to write that out. I don't want to have to remember that. All I want to do is go to y equals and see that it's there already. So what do I need? I need day 6. So if I want to plug in 6, that's an option, but not a fun one. So now that I have that in y sub 1, why don't I go to second table and go down to 6 where it tells me that it's 24,000. So my answer for day 6 is 24,000, so let's go back and answer it. All right, so our guy was 24,000. 24,000. So yeah, that's how you do it, exponential regression. The key there and the easy part there is that store equation thing, the store reg EQ thing, and hitting vars, going right, enter, enter. That makes life a lot easier. So try to remember that. You're going to be happy you did. Hope this helps. The function f of x equals x cubed minus 19.7x squared plus 91.74x minus 78.408 has a domain on x's in between 0 and 15 and including. At what x value does the graph of f of x change from decreasing to increasing? So this is obviously a calculator problem. And what I'm going to deal with is not only typing that in and graphing that, but also changing my window so that I can see all the action happening between 0 and 15. A regular calculator shows you -10 to +10. I want to see 0 and 15. So let's run to our calculator and see what that looks like. All right, so let's go to y equals and type our guy in. X cubed is going to look like that. Then I have minus 19.7x squared, so minus 19.7x. Here's the squared button, plus 91.74x, 91.74x, minus 78.408, so minus 78.408. What I'm trying to do is find out where this guy is decreasing to increasing. Okay, now what that looks like, and I'll try to demonstrate that here, is you're going down and then hitting a bottom and going up. Now, as I said a couple seconds ago, when I hit graph, it's going to give me stuff happening from -10 to 10. Obviously, I don't see everything I want to see. I want to see from 0 to 15, which shows up way over there. So I'm hoping that this goes back up. It's got to, otherwise this problem's defective. So I'm going to go to Window, and I'm going to change my x values from, let's do -1 just to be on the safe side, to 16 just to be on the safe side. Now, when I hit graph, I know that my graph is going to be like my picture is not going to be tall enough or it's not going to bottom out enough. See right there. So what I want to do is I want to change my window to change the y values too. So let's change the y min to -30 and change the y max to +30 and see if that does the job. Maybe it will, maybe it won't. Graph, no, it won't. So let's do it again. Now, if you're wondering, I know how to use these calculators. Why don't you hit zoom out? Because if I hit zoom out, that changes the x's, and I want to keep the x's the way it is. So let's do negative, no, not two negatives. That's impossible. How about negative? That looks like it went out a lot, so let's do negative 100. Maybe it's too much, but who really cares? What did I do? Oh, did I use the minus sign? I did. Negative. Learning lesson, kids, don't use the minus sign. Let's do 50. Not that we care about how high it goes. We care about how low it goes. Still not low enough. Man. So let's go to window and do negative 200. Hit graph. There we are. All right, so again, what we care about is where it goes from decreasing to increasing. So what we need is to find that local minimum right there. Local minimum. Now, how do I find a minimum value? Go to second, calc. There you are, minimum. So you can hit 3 or you can scroll down and there it is. Now it gives you a little blinky thing and we want to put the left bound on the left side of our minimum. So it's already there, so let's hit enter. Let's move to the right side of our minimum. There we go, there we go, there we go. Hit enter. And what this is saying is that your minimum is going to exist between these two areas. Now, if for some reason we weren't thinking and we put our left bound way over here, we're not going to get the area that we want. We have to make sure we have our left bound just to the left of our minimum and our right bound just to the right of our minimum. For guess, you always hit enter. I've never seen a time where guess was, important. But what we get here is our minimum happens at 10.10801. So 10.108 will do it. So let's go back and circle the option that gives us that. 10.108, the answer is C. So the way this problem is worded again is they want to go from decreasing to increasing, which means they want a local minimum. Oh my gosh, which is right there. If they were to say increasing to decreasing, you would do the same idea, but find your maximum. So it's all in the wording. And as you saw in the calculator part that we just did, we had to change our window quite a bit until I felt happy about graphing stuff. So if that's what you have to do, that's what you have to do. Part of learning how to use these calculators is troubleshooting those moments when you're not satisfied the second or third or fourth time. You go to window and try to figure stuff out. So, weird problem. The problem in general is not weird. It's just having to throw it in your calculator. That's the weird part. So hope this helps. The table gives values for a function m at selected values of t. Which of the following graphs could represent these data in a semi-log plot where the vertical axis is logarithmically scaled? All right, so I don't need a calculator here because I'm just given 3 graphs. Now, I had to make this problem with just an A, B, and a C because it's very hard to create semi-log plots and fit them all in one slide, so I didn't do it that way. Now, what you're looking for is a semi-log plot A where the vertical axis is logarithmically scaled. That's thing number 1. A semi-log plot where the vertical axis is logarithmically scaled goes like this, and as you work your way up, things get a little bit tighter. Okay, I could have done a much better job showing that. But what we see in A is the vertical axis is just linearly scaled. It goes up 200, then 400, then 600. That's not the guy we want. This is just a regular old coordinate plane. Now, B and C, those are our guys where it's logarithmically scaled, where we go from 10 to 100 to 1,000 to 10 to the 4th. Same thing over here, even though it's cut off. And as you can see, the horizontal parts are kind of squeezing in, just like I said it would. Now, the table is given, and the table is not giving us linear values. The table is giving us values that are exploding. In fact, it looks like you multiply by a 4-ish number every time. Not 4, maybe like 3 point something every time to move your way up. Okay, so this is exponential. I don't know exactly what that number is, but it's exponential. Okay, when these guys go up by 1s, this goes up by a multiple every single time. Now, on a log plot, if you have an exponential function, it would appear to be linear. And C gives me that. One more time, on a semi-log plot, if you have exponential values, the dots appear to be linear, and C gives me that. B gives me what looks like is quadratic or something like that. It gives me a curve. If you have a curve on a semi-log plot, you don't have an exponential function. So it's not going to be B. So although the temptation is to look at this and be like, oh yeah, no, it's exponential, so it should look like that, exponential growth. Yeah, it'll look like this on a rectangular plane, but it'll look like this on a semi-log plot. So one of those things where you only see semi-log plots really in AP Precalculus. I've never seen it anywhere else in my 20 years of teaching and extra 6 years of colleges. So take it for what it's worth. Semi-log plots, super important. But, hope this helps. Let g of x equals 9.651 cosine pi over 5.543 x minus 1.269, nice, plus 1.911, nice, on intervals 0, 10. Which of the following statements is not true? All right, so we need the lie in all of this. We need the lie. So obviously what I need to do is I need to run to my calculator because there's no way I'm doing this without a calculator. I'm going to y equals, I'm plugging that in. I'm graphing that on 0, 10, which is good news. And, seeing which one of these is not true. So let's go and see what happens. All right, let's graph this really gross equation. We've got y equals 9.651. Here's my cosine. It automatically pops up a parentheses. I'm really paranoid with fractions, so I'm just going to put a parentheses there for the fraction. Probably not necessary, but I don't know. I'm afraid if I don't do this and I attach x, it's going to think that like my x belongs in the denominator, which I definitely don't want it to go. So that's me plugging that in. That's me ending the fraction, and that's me putting in x. Now I need to subtract 1.269, so minus 1.269. I'm going to close that parentheses, and I'm going to add 1.911. Let's hit graph and see what we get. All right, so we have a peak just outside. We only care about stuff between 0 and 10, so I'm going to fix my window. I'm going to change the y min to -1, okay, because I'm going from 0 to 10, but I always like to have that little bit of cushion. It goes to 11 for my x, okay. I need to add more stuff to the y, so I'm going to change the y max to 13. I don't know. That should do it, though, I think. Yeah, that should do it just fine. Now, I only care about stuff between here and 10, which is right here. So I need to find the lie. So let's see if A is true. The minimum value occurs at x equals 7.782. So I need to find the minimum value, which is going to be right there. So to find a minimum, we go to second calc. There's the word minimum, so we can hit 3 or scroll down and hit enter. In order to calculate the minimum, we've moved my cursor just to the left of the minimum, and then move it just to the right of the minimum for right bound. And then it's going to give me a spot where it says, my answer, my minimum, is going to be in between these two. Guess is always enter. I've never seen a time where it's never that. And my minimum occurs at x equals 7.782. So A is true. That's not the lie. A is not the one I want. So let's keep going. The maximum value occurs at y equals 11.562. So here's my maximum value. We're going to do the maximum the same way we did the min, but we're going to do 4, which is maximum. So let's go all the way to the left of that maximum value. There you are. For left bound, make sure you're to the left of it. Hit enter. For the right bound, make sure you're just to the right of it. Hit enter. And for guess, hit enter. And we care about the y value, not the x value. That's the trick behind this problem. The y value is 11.562. Sure is. So B is a true statement. So we need to keep going because the answer is not A and the answer is not B. The midline is the equation y equals 1.911. Now, I do not need to do anything on my calculator here because I find my midpoint by seeing what is added or subtracted to my entire function. So I have blah, 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 cosine, blah, 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 close parentheses. The number that's floating around right after that is my midline. So C is a true statement because my midline is 1.911. So D has to be a lie. Let's find out why. The graph is concave up at x equals 3.281. So let's go back to our graph. 3.281. Here's 1, here's 2, here's 3. So here's 3.8. And at that moment right there, that's concave down. It doesn't start going concave up until we hit the midline. Now, if you're paranoid and like, well, how do I know that that's not like 1.2 or something like that? Well, if you want to find out what the y value is, and if the y value is greater than the midline number, which is 1.911, you can hit second calc and type out your value at 3.281. 3.281. And since that number is much bigger than 1.911, that number occurs above the midline where it just so happens to be concave down. So after all of that, of course, it was problem or option D that was the lie, and we want the one that is the lie, so we are going to circle D. Oh boy, so much fun. The answer is D. Again, we wanted the lie. You were true. You were true. I didn't even need a calculator to see that you were true, but you were the one that was a lie because it happened like right around there. So that's concave down. So yeah, lots to do in that problem, but it's a tricky one, and we did it. Hope this helps. The function f is defined by f of x equals a sine b x plus c close it plus d. This is the typical sinusoidal equation function where your amplitude, your frequency, your horizontal shift, your vertical shift for constants a, b, c, d. In the xy plane, the points 3, 4, and 5x represent a minimum value and a maximum value respectively. On the graph of f, what are the values of a and d? Now, I'm not going to use a calculator here. There's a thing in your calculator called sine reg, and maybe this will do the job for you, but I'm not sure if you can only do sine reg with 2 points. I'm going to envision this without the use of a calculator. It tells me that you're a minimum and you're a maximum. So if I graph that, right, and it's all above here. If I graph that and my minimum is 1, 2, 3, and my maximum is at 5, and it happens at 4, and it happens at 8, it's going to look something like this. Okay? And there's not a ton, but we only need to find 2 things, A and D. Now, I said it a second ago, but I said it pretty quickly. I care about A, I care about D. Now, why I'm circling A and D and doing weird things with it, because I already started it and I don't feel like stopping. A stands for amplitude. Amplitude. Amplitude is half of the total height. Okay? Now, if I look at my total height here, I go from 4 to 8. So half, let me see, 8 minus 4 is 4. Half of 4 is 2. So my A is going to be 2. So that eliminates this guy. Now, what does D stand for? D stands for the midline. D stands for the midline. It's the area that cuts my line in half. But specifically, in the way you can get that numerically is whatever the low point is and whatever the high point is, it's literally half of that. So drawing this out, we can see that it's 6. If you were given terrible numbers and asked to find the same exact thing, you would do your minimum value plus your maximum value and divide that by 2. Midline is just like a midpoint where you add 2 things and divide by 2. So that gives you 12. 12 over 2 is 6. So your midline is 6. So D equals 6. So we need the one where A is 2, D is 6. It's going to be in sync. But again, one of those problems where you didn't really need a calculator. And again, sine reg, oh boy, sine reg, that's something we don't want to do. Sin regularly? Anyway, sine reg, I'm not even sure if that would work with 2 points. So I'm not even going to try it. I'm just going to stick with my own brain, the human calculator. Hope this helps. This is going to be terrible. Let P of x equals 3x to the 4k minus 111 all over e squared plus 3.3. K represents an integer. If P of 2 equals 61.465, find P of negative 1. So this is what I'm going to do. I'm going to run to a calculator, come back here, and then run back to a calculator again. What I need to do first is it just told us that if I were to plug in 2 for x, because, P of x, P of 2 means x is 2. If I were to plug in 2 for x, I'm going to get 61.465. Okay, so let's actually do this. Let's see what I can do without the use of a calculator first. I might regret this, but in doing this, it might make my life a lot easier. Okay, maybe. I don't know. Again, if I plug in at 2 for x, I get that number. So I'm going to rewrite this equation and say instead of p of x, 61.465 equals 3, and I'm going to put parentheses here because why not, 2 to the 4k minus 111 all over e squared plus 3.33. Now my job is to get k all by itself. I'm going to multiply both sides by whatever e squared plus 3.33 is. That allows that to go away. So e squared plus 3.3, just 3. I think I said 3 before, but it's just that. All right, so now what I have is e squared plus 3.3 times 61.465 equals 3 parentheses 2 4k to the 4k minus 111. Let's add 111 to both sides. Add 111 to both sides. So now I have e squared plus 3.3 parentheses 61.465 parentheses plus 111 equals 3 parentheses 2 to the 4k parentheses. All right. Divide both sides by 3. Divide both sides by 3. And just to make life easier, that makes u, and u go away. I think we're all good with that. This is going to be the nightmare. I'm going to have to log base 2 both of these. Log base 2, log base 2. Now, if I log base 2 to the 4k, what happens is that goes away and 4k drops down. So that goes away and 4k drops down. So let's get rid of that and just put 4k here. And if you're like, oh boy, are we done yet? Now I take this whole thing and divide it by 4 because I have to divide this by 4 to get k all by itself. So after all of that, I'm going to pray to the God that I serve that I type this whole thing into my calculator correctly. That'll give me k. And if you're like, hooray, then we're going to be done, right? No. We are not going to be done because once I have k, then what I have to do is plug that k into this equation and then plug in -1. Oh, we're only halfway done, boys and girls. So wish me luck. Let's plug this into our calculator and see what god-awful number we're probably going to get. Buckle up, baby. You're in for a wild ride. So we have a huge fraction, and the fraction is that huge log thing, as you can see on the right. That's the numerator, and then the denominator is 4. So I'm going to wrap the entire numerator in parentheses. Okay, now there's a little secret for log that if you hit math and scroll up a few times, there's log base. Okay, what that does is it allows you to plug in log base 2. See, before you would have to do the change of base formula. Not anymore. Now what I have is a really big fraction, and with really big fractions, I like parentheses. So I have another parentheses. I'm going to type in e squared, so I could use, I guess, where's my e to the whatever? So second e to the whatever squared. Let's move over. Plus 3.3 close that parentheses, 61.465, close parentheses, plus 111. Ooh, that was a close one. And close that parentheses. So I have left 1, 2, 3 open. Now I'm back to 2 open. Now I'm at 3 open, 2 open, 1 open. So I need to put divided by 3 and close it. Now I take all of that and divide it by 4. And close that. And I get the number, you've got to be kidding me, 6. After all of that, I get 6? All right, I'll take it. Let's go back and use it. Now, remember, this gives us k. So k is 6. So let's go back and deal with that. Well, who'd have thunk it? After all of that, k is 6. So this is what I need to do. I need to do this again and replace k with 6, now that I know that k is 6, and then plug in -1 for x. So in my calculator, I'm going to plug in 3 times -1 to the 4 times 6, so to the 24, minus 111, all over e squared plus 3.3. So let's do that and see what happens. All right, so just like I said before, I'm paranoid about fractions, so let's put a parentheses there. 3 parentheses -1 to the 4 times 6, so I'm just going to put 24 because I don't want to risk screwing something up. Minus 111. Close that parentheses. Divided by, open parentheses, e squared, so let's do this again, second ln squared, plus 3.3, close it, and we get -10.1037, so -10.104. So let's go back and select that one. All right, well, that was awful. That was awful, but after all of that, we got it. So, yeah, I mean, this is one of those problems where the kids who get the 5s might get this one correct. It's really difficult. I mean, look at it. It's not fun, and it's awful, and it's the 35th problem that you're doing on a 40-problem multiple choice exam. So if you get to this point and you're like, well, this stinks, yeah, I don't blame you. But, we did it here, and maybe you'll see one like it. So I hope this helps. Two function models K and M are constructed to represent the population of deer in a forest. Both K of t and M of t represent the population of deer after t years for t is greater than or equal to 2. Interesting. I wonder if that's going to come into play later. If k of t is 200 minus 30 ln of t, and m of t is -5t plus 200, what is the first time t that the population predicted by the logarithmic? By the way, k is the logarithmic, and a model will be 10 years less. Ooh, look at me emphasizing that word with a bold font. 10 years less than the population predicted by the linear model, which would be m. You're the linear model. So I need to see when k is 10 less than m. So basically what I'm asking you is, when is k of t 10 less than m of t? Well, this is what I'm going to do. I'm going to run to my calculator, and I'm going to type this in the y sub 1 part. So I'm going to, in my calculator and in my TI-84 plus, I'm going to type in y sub 1 equals 2 hundo minus 30 ln of t. All right, pretty simple. In my y sub 2, I care about when this is 10 less than that. So basically, if I have -5t plus 200, I want this to be 10 less than that. So I just subtract 10. So basically what I do is, in my graphing calculator, I don't want 200, I want 110, because I'm making an adjustment. So let's run to our calculators and see what happens when we take care of that. And by the way, what I'm going to do is I'm going to run to my calculator and find the intersection of these two lines. So let's do it. All right, let's do it. We have y equals, and we're going to type in just what I said we'd type in, 200 minus 30 ln of t. So here's my ln button. Of course, it's not going to be t, it's going to be x, but we know what to do. That's the first equation. The second equation is going to be negative 5 instead of tx plus 1,900. Now, since we are dealing with a 200 that's floating around in y sub 1 and a 190 that's floating around, those are y-intercepts. So I'm not going to hit graph and expect to see anything. So what I could do whenever I don't see anything, usually something that kind of works, is going to be zoom fit, which, I scroll up to 0 or I just hit 0 and hit enter and zoom fit. Now here's the thing. Let's just make believe that I'm blindly going to do this and not think at all. Okay. If I go to second calc and hit intersect, right? And I'm going to think, oh, okay, well, there's an intersection right there. Let's plug it in. Well, all right, let's do it. Let's plug it in. Let's go to the first curve, hit enter just to the left of it. Let's go to the right of it and hit enter just to the right of it and hit enter again. I get 1.922. And I'm like, oh, great, 1.922. That's awesome. Now, here's the issue. Do you remember in the original problem, t is supposed to be greater than or equal to 0. This isn't greater than or equal to 0. This isn't my answer. Now, if I notice my graphs, okay, this is the ln1, okay? And if you look back, since it's negative ln, that's why it's curling down like that. It's doing the mirror reflection over the x-axis. This is the linear guy. This is probably going to keep going down and to the right, and this is going to keep leveling out. And so these guys are going to intersect again off here, off screen. So what I need to do is maybe I just need to hit zoom out a little bit and see if I get another intersection. Oh, look at that. Another intersection, just like I predicted. So this original guy isn't going to do it. So we have to hit intersect again. So second trace intersect. Let's go over here, make sure I get close enough, but not too close, just to the left of it. Hit enter. Let's move just to the right of it. Hit enter, always hit enter for guess, and it's giving me 13.7077, so 13.708 should be my guy. So I'm going to run back to my calculator, hit 13.708, and get my answer. Tricky, 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 tricky problem. This was a tricky problem. First things first, it couldn't be simple where they were just like, hey, find out when these guys are equal to each other. They had to throw this part in there. Then they also had to throw this part in there. So it's a tricky problem. So be prepared for tricky problems like that guy right there. Hope this helps. How many complete cycles will y equals 4 sine 4x minus 3 sine 6x complete on the interval 0 is less than or equal to x is less than or equal to 100? So, ugh. All right, well, this is what I would do. The last thing I want to do is graph that. And I know whenever I have like weird things like this, it's not going to be like, ooh, all pretty and stuff. It's going to be like this, where it kind of goes back and forth, almost like a heart rate thing. Of course, it's never going to look like that. I just don't know how to draw. So what I'm going to do is I'm going to graph this in my calculator, all right, and find out how long it takes for one period to occur. Okay, so if it goes up and down and then slows down and then repeats the process right around here, I'm going to find out what one period is. Once I have one period, say it's 10, it's probably not, but say it's 10, then what I'll do is I'll just divide 100 by 10 and get how many times it repeats. Watch it be 10. I actually don't know, but let's see what happens, and maybe it is 10, and maybe I've just wasted a whole bunch of your time. Not my time, YouTube money. Let's go to our calculator. Y equals 4. There's my sine 4x. Close parentheses. Minus 3 sine 6x. Now this is what I'm going to do. I'm going to hit window before I graph this. actually, I'm sorry, zoom before I graph this, and zoom trig. Usually that gives me friendly pi-ish numbers. Maybe it will here, maybe it won't here. I don't know. Let's see what happens. Okay, I hated that. I hated that a lot. So why don't I not do that? And why don't I change like a window from like 0 to, let's do 2 pi, just to see what happens. Maybe that window is not good enough. A lot of what we're doing is kind of like seeing a window that works for us. That is much better. Okay, that is much better. It looks like what's happening is we start kind of like at this weird thing, like at this almost negative coast looking thing, and then way up, then down, then way up, then kind of down, then it repeats at that guy right there. Now let's use common sense. Since the window I created was 0 to 2 pi, it seems to repeat right here in the middle of 0 and 2 pi. This is going to come as a shock, but that number in between 0 and 2 pi is pi. Now, if you're ever uncertain as to where things are, you can always do an intersect, or you can always do second calc and do a 0. But I'm fairly confident that that number right there is pi, since that number right there is 2 pi. So I'm going to go back and finish the problem, and I'll probably have to come back here again because the numbers are going to be gross. But now that I know that my period is pi, that makes the problem a whole lot easier. Okay, so as you could see, the period was pi. Okay, not pleasant, not fun, but the period was pi. Now, the last thing that I said before that I wanted to do is try to count how many cycles happened during that. So what I'm going to do instead is I'm going to run to my calculator and find out what 100 divided by pi is. Now, before I do that and circle my answer, it wants to know how many complete cycles will occur from the beginning to the end, from 0 to 100. Now, I'm definitely going to get a decimal here. No matter what decimal I get, I'm going to round down because I have to complete a cycle. So let's just make believe that I get some number like 9.99. Did I complete a 10th cycle? No. So the answer is just going to be 9. So that's not what's going on. But let's just make believe that is what's going on so I can go back to my calculator and see what happens. All right, so 100 divided by, that is not the button I wanted to hit. Start over, start over, start over. All right, so 100 divided by pi, which is second caret thing, is going to give me 31.83. Who cares? As I said previously, we're rounding this guy down. So let's round it down to 31, go back and circle the answer, and I'm done. Okay, so we got 31 point who cares, which means no matter what, we round down to 31 because we're completing cycles. If I were smart, I would have made 32 an option. But I guess I'm just not smart. I don't know what I'm doing. Either way, weird problem. Hope this helps. The graph shows a piecewise function j of x. If h of x represents the inverse of j of x, what is the maximum value of h of x? Oh, cool, a calculator problem that we don't need a calculator for. It's happened a few times if you're watching all of my videos, and this is where it happens again. I don't need a calculator for this. Why it's in the calculator section, I don't know, to confuse you. But what I have is I have a regular function here, and I care about the inverse. Now, I am not an artist. What I don't want to do is I don't want to graph this just by looking at it. So let's use the idea of what an inverse actually does. First off, this is j of x. Okay, so let's write out a table for j of x using what looks like the 4 dots that I have. So I have x, I have j of x, and I have 0, 0. That's an obvious point. I have 4, 4. That's an obvious point. I have 5, 3. That's an obvious point. And I have 8, 9. That's an obvious point. Now, the first step in finding an inverse is swap the y and the x values. So why should that change here? So 0, 0 swapped becomes 0, 0. Good job. 4, 4 swapped becomes 4, 4. Good job. 5, 3 swapped, finally a change, is 3, 5. Good job. And then 8, 9 swapped is 9, 8. Now this is my h of x function. Now, if you wanted to graph it, you could dot here, 3, 5 is a dot here, and then 9, 8 is a dot here. So you would connect these two. Now, by the way, if you're like, why hasn't it changed here? Graphically, the inverse is a reflection over the y equals x axis. This part right here is the graph y equals x. So this is a reflection, so nothing changes. Now we finally do have a reflection. And oh, please let me graph this well. Nailed it. Now that was extracurricular. I didn't need to do any of that. What I really needed to do is, now that I have h of x, I just needed to find out the maximum value, and that maximum value is 8, not 9. 9 is not a maximum value. When they talk about maximum values, they mean the maximum value that shows up on the y-axis. Okay, so in this case, it's going to be 8C is my guy. So we did a little extra here, but you know what? I had fun. And look at the pretty little drawing we made. It looks like a arrow with a disability. 39th problem, or 38th problem. Oh gosh, hope this helps. Let d of x equals 4 point sine, parentheses, 2.51x minus 2, close it, and b of x equal d of x, which is that, plus 2.5. Which of the following is not a 0 of b of x on 0 pi? All right, well, b of x is just d of x added to 2.5, so let's change that. We care about b of x. It would be nice if I had the pen. B of x is now going to be 4.5 sine 2.51x minus 2, in parentheses, plus 2.5. Okay, so all I did was rewrite d of x, add the 2.5. I just added the midline there. So what I need is, I need to zero in on 0 to pi, and I need to graph this on a graphing calculator and find out which one of these is not a 0, which means 3 of these will be. So let's go to our calculator and see what happens. All right, so we've got 4.5, we've got sine, we've got parentheses, 2.51x minus 2, so 2.51x minus 2, close it, but now I'm adding 2.5. So I care about when things happen between 0 and pi. So why don't I just run to my window and make the x min 0 and the x max pi? Okay. Since I'm lifting this up 2.5 and my amplitude is 4.5, this will go up to 6, so we'll put you at 7. This is not necessary, by the way. This is me just adding stuff. And let's go down to -5. That way we get a little bit clearer or zoom in version of what we're dealing with. See what I did? It wasn't necessary to change the y min, but changing the x min and max made life better. So 0 number uno, 0 numero 2, and 0 option D is right there. I made a joke. Came from like Home Alone or something like that. I need to find all 3 of these zeros. Now, you might be able to look at these and say, I know my answer already, it's B. Great. But let's just make sure we know what we're doing. If I want to find exactly what the values are for 0, you hit second, calc, and go to 0. All right. Zeros are where your line or curve crosses the x-axis. So to find the first 0, I go to the left of it for the left bound, hit enter. Go to the right of it for the right bound, hit enter. This guy tells me that my 0 exists in between the 2 little arrows, which is correct. Always hit enter for guess, and we get 0.562, which means A is a 0, which means A, we're going to cross it out. Now to find the second one over here, which is going to be 2 point something, we hit second calc, we hit 0 again, we go all the way over here just to the left of where it crosses the x-axis, hit enter. Let's go to the right of where it crosses the x-axis, hit enter. For guess, hit enter. And now C is no longer an option that I want because 2.283 is a 0 and I want the one that is not a 0. So let's find this 3 point whatever it is. Second calc 0. Let's go just to the left of it, just to the right of it, in the little space that I have. Hit enter, 3.065. So it looks like the guy that wasn't my guy was 2. Again, could I have noticed that immediately without having to do the 3-0 things that I just did? Yep, but I wanted to show you that just in case you run into a problem where you need to find zeros and you're just going to have to do the process anyway. So let's go back and circle C. No, circle B. Oh, wait, no, circle B. Ugh. Let's go back and circle our answer. If only I knew how to speak. The answer is B. And again, we could have noticed that without having to do the zeros thing, but it was good for you. It was good for me, that's for sure. Speaking, though, I'm just not good at. It's too late in the evening for me. And too late in the test, because this is problem 39, which means we have one more multiple choice to go. So hope this helps. A water wheel spins clockwise at a rate of 90 complete revolutions per 60 minutes. The radius of the water wheel is 12 feet. The center is built 8 feet above water level. One of the spokes of the water wheel is painted green. Which of the following sinusoidal functions models the height of the edge of the green spoke h with respect to time in minutes denoted as m? So this is a calculator problem. I ain't going to use it. Sine reg here, which is, sinusoidal regression, just like linear regression, just like quadratic and exponential, all that stuff, ln reg, I guess you could use it. But it's sine reg you're going to want to use when you're given a bunch of points. I'm not given any points here, so I'm not going to use sine reg. So I'm going to use my human calculator, my brain. Now, I like to create a picture whenever I deal with these and use that picture as my guide. What do I have? Well, the green spoke is right here at the middle. Okay, so I have a midline, and my midline is 8 feet above water level. So my midline is going to be at 8. So let's put an 8 right there. There is my midline. Hooray. Now, whenever you're given a sinusoidal problem and you are given a radius, that radius is your amplitude. So what's going to happen is as this guy turns counterclockwise, you're going to hit a tippy top. And that tippy top is going to be the length of the radius. So 12 plus that radius is going to be 20 feet up in the air. So that's going to be my maximum, is 20. As this guy goes underwater, it's going to go under 12 taken away from 6, which means it's going to bottom out at -4. And if you're thinking, whoa, buddy, you can't have negatives for real-life sinusoidal problems. You sure can if you're going underwater, and this looks like it's underwater to me. So I'm going to go with that. Now, as this rotates counterclockwise, you are starting at the midline and moving up and then down, and then up and then down. So you're starting at the midline and you're moving up and then down and then up and then I'm out of space. Okay. Now that to me looks like a sine. A sine, I know here it starts at 8, but a sine starts at usually the x-axis, or in this case the midline. It starts right there at that origin point and goes up and down and up and down and blah, blah, blah. So this is sine. So, I guess we have no choice, but it is sine. Now, what this means is as I start to build this equation, I know one thing I don't have. Now, what I do have is I have an amplitude. I have a midline. What I need to do is figure out what my period is. Now, if I'm looking at all this and trying to write an equation, I'm comparing it to y equals a parentheses sine parentheses b parentheses x minus c, close it. Actually, I really don't like that parentheses there. Let's get rid of you. Close it, and then plus d at the end. Okay? Now, what's what? Well, you're my amplitude. I already know that. So my amplitude is 12. You're my midline. I already know that. What I also know is since this is starting at sine, I'm not going to have a horizontal transformation or translation. I'm not going to move left or right anywhere. Okay, so that minus c is useless. What I don't have is b. B is the frequency. B is not the period. I'm going to have a hard time trying to figure out using these numbers what the frequency are. So what I'll do instead is I will find out what the period is. Now the period lives right here where it starts over. If this guy is going to do 90 things in a course of 60 minutes, that means this number right here is going to be 60 over 90, which is 2/3. Now, does that mean I'm going to do 2/3 here? No, that's not even an option. That's my frequency. The way, actually I do, well, I don't, it's 90 over 60. Oh, that was a close one. What I need to do is I need to find out what my frequency is. Now, my frequency is found out by doing 2 pi over the period, which is 2/3. Okay, multiply the top and the bottom by 3 halves rather, it's reciprocal. So that crosses out, that crosses out, that crosses out, that crosses out. I now have 2 pi times 3 over 2, so the 2's cross out, and I'm left with 3 pi. So my period is 3 pi. So putting this all together and using h of m and using m instead of x, I have h of m equals 12 sine 3 pi x, because I don't have a horizontal translation, or m plus 8. So that's problem number 40 in our multiple choice test. Okay, could I use a calculator? Probably, but I just, I didn't want to because I didn't need to. And sinusoidal regression is just not fun if you don't have any points. This, however, is fun. So 40 problems down. This is a typical practice test, what it would look like. Hope this helps. Yes, we made it to the free response questions. There's going to be 4 of them on the AP exam, and usually each problem has like 5 or 6 parts to it, and this is not going to be any different. You'll have problems on trigonometry, data modeling, calculator problems, non-calculator problems. This is problem 1. This is a calculator problem, and this is data modeling, so this is 6 parts, I believe. Let's just jump right into it. Consider the function h of x as depicted in the provided table. So there you go, with a domain consisting of the values 1 and 2 and 3 and 4 and 5. Additionally, we are presented with another function, j of x, defined by j of x equals 5 log of x. So we'll probably need our calculator for a lot of these. Define the function k as k of x is j of h of x equals j of h of x. Determine the value of k of 4 as a decimal approximation, or specify if it's undefined. When would it be undefined? Like if x is negative or something like that. So let's see what we need. We have k of 4 they want. Okay, and again, this is part I, part 1, part I. K of 4, I'm going to use this version of it, equals j of h of 1, and let's get different colors because I can. So let's see what we have. H of 1 is found by taking the 1 in this guy and saying, oh, well, 1 maps out to 7, so h of 1 is 7. So this becomes j of 7. Now, how do we find j of 7? We're going to need our calculator for this one. So j of 7 is going to be 5 log of 7. Now, by the way, just in case I haven't said it or you haven't noticed it, this is invisible base 10. So yeah, you could pretty easily plug this into your calculator, and that's what we're going to do right now. All right, 5 log 7. Again, the log that we saw in the problem is the same log that we see here, invisible base 10. Going to get a pretty terrible number, 4.2254, so 4.225. Remember, when we do these, we round to 3 decimal places. So 4.225. Let's go back and write that out. All right, so k of 4 is going to be roughly 4.225. So that's it. That's all we have to do. Now, again, I know I said it in the calculator thing. Since this is an open-ended, we have to make sure that we round to 3 decimal places. So this is our approximation rounded to 3 decimal places. So that is part I. Now, part II, or E for Joel Embiid, because he has 2 I's in his name, Philly fans? Determine all values of x for which h of x equals 7, or specify if no such values exist. Now, the h is this guy. So, what x values give us h of x equals 7? Well, there's 2 of them. Now, this is not saying, hey, let's plug in 7. No, this is saying this is h of x equals 7 right here. So your 7 and your 7. So what x values seem to do that? 1 and 5. So x is going to equal 1 and 5 for this guy right here. Okay, so no calculator. This one was one of the simpler ones, so I'll definitely take it. Okay, problems 1 and 2 of part A complete. Now let's take a look at problems 1 and 2 of B. Consider the function h, it's the same thing, I don't know why I'm reading it. Discover all the values of x as decimal approximations for which j of x equals negative 7.5, or indicate if no such values exist. So this is me taking the j guy and replacing j of x with negative 7.5. So negative 7.5 equals 5 log of x. So what I need to do is solve for x here. Well, x is trapped inside of a log. All right, x is trapped inside of a log, so what I have to do is I need to get log all by itself so I can get x all by itself. So if I divide both sides by 5, that gets the log all by itself. Okay, so this is actually negative 3 over 2. Now, if you didn't know that, this is a calculator section. By all means, use a calculator. You can write that out as negative 1.5, but I'm just going to keep on going. That's going to equal log of x. Now, again, log of x means invisible base 10. If I want to get x all by itself, I can take the 10 to the of both sides. Bad grammar? Absolutely. You could just write this out in exponential form, but I prefer doing it this way. So x is going to equal whatever 1 over 10 to the 3 halves is. But what it is it's not going to be a pretty number. At least I don't think it is. I mean, no, it's not going to be a pretty number. I'll just stop right there. So let's run to our calculator and find out what 10 to the negative 3 over 2 is. So 10 to the negative 3 over 2. The nice thing about these guys is it actually gives you 10 to the right in front of log, or right with log. I wonder why. Negative 3 divided by 2 is going to give us 0.0316. So 3 decimal places is 0.31 or 32. 0.032. I don't know if I said that correctly, but that's what we're going to write out. 0.032, that's going to be our guy. 0.032. And if you're wondering why is it so ugly, well, when you have a number taken to a negative exponent and that negative exponent is greater than 1, it's just not going to be the prettiest thing ever. This is asking you 1 over 10 cubed, but then take the square root of 10 cubed. So 1 over the square root of 1,000, big number. Okay, so 1 over a big number is going to give you a small number in the end. Now here's where we have to just double check things. Can I take this, since this was j of x, plug that in, can I take 5 log of 0. Blah, blah, blah? Yes, I can take the log of any positive number as long as it's not 0, as long as it's not negative. This is awfully close to 0, but it's not 0, so this will work just fine. Okay, so yep, this is allowed. Values do exist. I get one answer, and that's my one answer only. Now it's 2. Ascertain, that's a word you don't see often. The end behavior of j of x as x increases without bound. Express your answer using the mathematical notation of a limit. Now, if you need to graph this out, go ahead, be my guest, graph this out. Go to y equals 5 log x. The reality is this is nothing fancy at all. This is a log function multiplied by a positive number, which means it's just going to be a warped version of a log function. Log functions look like this. Okay, everything, remember what I said a second ago, you're not allowed to have negatives, you're not allowed to have zeros. So a log is going to hover awfully close to the y-axis and then go like that. It will never at any point touch the y-axis. It'll never cross the y-axis. It's always going to stay to the right side. Okay, so the end behavior of one of them is going to be obvious. As we move to the right, as we increase without bound, this is going to continue going up and to the right. So the right side, okay, the limit as we keep moving to the right, the limit as x approaches infinity of j of x is going to also be infinity. Okay, if you're wondering, well, won't that flatten out somewhere? No, it will never flatten out. Now, what's going to happen is, yes, this will continue to get flatter, but it'll still keep going up and to the right. It'll never at any point stop going up and to the right. Okay, it'll really do it slowly, but this will continue going up and to the right, meaning that it'll be infinity. Now, if you're thinking, all right, the limit as x approaches negative infinity, you're wrong. See, we can't go to negative infinity. We can't. I mean, we keep going left, and we hit this roadblock right here at the y-axis. So the y-axis, we can't go any further than that. In fact, since the y-axis represents an x value of 0, we can't even hit the x-axis. But what we can do is we can approach that 0 from the right without actually touching it. So we're going to say the limit as x approaches 0 from the right of j of x. Now, as we approach 0 from the right, we're going down, 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 down forever. Okay, and this kind of is obvious here as we have a small x, we're hitting negative numbers. So this is going to be negative infinity. Okay? So that's the end limit of a logarithmic function. Remember, the end limit of logarithmic functions are never going to be limit as it approaches infinity and as it approaches negative infinity. You're going to have to hit a roadblock somewhere, and that's what we did with this guy. All right, so part B, dendo. Let's do part C. Consider, I keep doing that. Determine if h possesses an inverse function. All right, I'm going to tell you this and tell you this right now. When I was looking at the practice examples of these, you are not allowed to say it fails the horizontal line test. Now, if you're like, whoa, what's a horizontal line test? If I were to graph these points, right, I get 1, 7, 2, 4, 3, 1, 4, 4, and 5, 7. Okay, now you know what the vertical line test is. The vertical line is you draw a vertical line, you pass it through your function, and if your vertical line hits a spot more than once, it's not a function. So if we were to flip this sideways, which it would be, like the inverse of this would be dots going like this, okay, because you would just flip the functions. I'm sure we're going to do that at some point. If you're thinking, oh, well then, if we were just to make believe that this is going to turn into this, why wouldn't the horizontal line test hitting 2 dots not be good enough? I don't know. But for whatever reason, you're not allowed to say it's invertible because it fails the horizontal line test. You're not allowed to say that. So what we will say is we will say something like this. Okay? We have the 5 points of h inverse of x will be, and I'll just take these and I'll flip them around. So it's 1, 7, 2, 4, 3, 1. In order to find the inverse, you literally swap the x's and your y's. So our 5 coordinates will be 7, 1. Maybe I should say coordinates instead of points, but there's nothing wrong with saying points. It just sounds more professional, I guess. 1, 3, 4, 4. and 7.5. Since an x value of 7, I'll just say since an x equals 7 is not 1 to 1, H inverse of x is invertible, or is not invertible. Okay, so again, it's not good enough to say, I did the horizontal line test and the horizontal line test failed. You have to explain what it means for the horizontal line test to fail. 7 maps to 2 different numbers after I flip them. 7 maps to 1 and 7 maps to 5. A function cannot map to 2 different y values. Therefore, H inverse is not a function, which means it's not invertible. I don't like it. I don't like that the AP people decided that, yeah, not good enough, friend. Don't like it. But that's what they decided, and I can't help it. I don't make these tests. Now, I make this test, but I can't make these tests. So something to look out for. Provide rational, you're kidding me. So all I had to do for 1 was just say no. That's really annoying. So let's try this again. And this is a good learning experience because by drawing a rough draft, it allows me to maybe write this a little bit better. So I'm okay with this. Determine if H possesses an inverse function. It doesn't. Okay. End sentence. Now, what does that provide? A rationale for your response to this one. All right, let's word this better. 5 points, or 5, I didn't like the word points last time, so I'll change it to 5 coordinates of H inverse of x are, and I'll write it out as, again, 7, 1, 4, 2, 1, 3, 4, 4, and 7, 5. Now, I want to expand a little bit on what I said. The point, or the x value of 7 maps to both 1 and, what's the other one? 5. Therefore, H inverse is not a function because it is not 1 to 1. Okay, this one's 1 to 2. And you could have used the 4s if you wanted to as well, but I like this explanation a little bit better. So a blessing in disguise. And also, as I started to write this out, I realized I was running out of room and I kind of wanted to rush my description. So I'm happy with this. But this is an example of what a problem could look like. You have some modeling, you have some inverse stuff, you have some other stuff, some calculator stuff that we had to deal with. Not all calculator, just a little bit. But, you know, something to expect. All right, so that's problem 1. Hope this helps. Welcome to Free Response Question Numero Dos, or FRQ2, as the kids on the street say. No one says that. This is a problem where a calculator is allowed, and we're just going to get right to it. Imagine a biologist conducting research on a particular species of bacteria in a laboratory setting. So close your eyes and imagine that. In 2018, where T is 5, time is 5, the biologist observes 200 bacteria. By 2024, this year, where T is 11, the population had grown to 800 bacteria. The population of this bacteria species can be described by the function b given by, an exponential function, where b of t represents the number of bacteria in year t. Usually when you're dealing with some type of growth or a population growth, it is going to be exponential, and so that should not come as a shock here in any way whatsoever. So, A and B are just some numbers we need to figure out. B of t is the total population after t amount of time. So use the given data to create two equations for finding the constants a and b in the expression b of t. So what part A I is asking for is come up with two equations, like a system of equations. Well, in order for me to come up with the equations, I have to take some of this information that I have right here. So what I do have is that when t is 5, I have a population of 200. So that gives me the coordinate 5, 200. So using that information where 5 represents t and 200 represents b of t, I can come up with the equation instead of b of t equals ab to the t, I can come up with the equation where I substitute b of t with 200, a is I don't know, b is I don't know, and t can be 5. So that's one equation. Now, if you're like, oh, I think I know what's going to happen next, you're probably right. We have another coordinate that's 11 and matches up with 800. So I have 11, 800, and that gives me the equation, replace b of t with 800, a is I don't know, b is I don't know, and replace t with 11. So what we have here is a system of equations, and I can use that system of equations to help me solve for a or b, which is something that I absolutely don't want to do in this situation, but I could if I really wanted to. Now, what I'm going to do instead, since this is a calculator problem, I'm allowed to use my calculator. I'm going to do 2 by using exponential regression. Now, exponential regression is something that you could do in your calculator that gives you something in the form a times b to the t. So I can run to my calculator, I can type all this information in, it's going to spit out some probably gross numbers, but I'll be all right, and then we'll write that down once we're done. Be right back. So exponential is going to start out just like any regular regression problem. So we go to Stat, Edit, and we type in our points. We had 5 matching up with 200. We had 8 matching up with, 11 matching up with 800. Got those backwards. Could have been dangerous. Now, what we do when we're done with our 2 points, and that's all we have, is we go to Stat, Calc, all the way down, I think, to 0 is exponential regression. Yep. So 0 is exponential regression. Now, since I'm going back and forth from my notes to a calculator, I'm not going to store this regression equation because it won't work for me. It'll disappear by the time I go back the way that I'm recording this video. So I'm going to ignore that. I'm going to hit calculate, and it gives me something awfully gross. Unfortunately, it's not 63. It's 62.996 and 1.2599, so 1.260 is going to be my guy. So I'm going to go back and use that information right there to come up with my equation. All right, so we ended up with y equals blah, blah, blah to the x. Well, I'm not going to write out y equals. I'm going to write out b of t equals, it was 62.996 times 1.260 to the t power. Now, I could have come up with those numbers using this method, but you could see why I wouldn't want to use substitution or elimination or whatever god-awful mess it would be. Log would be involved probably. I don't want to deal with that, so I'm not going to deal with that. Okay? All right. Part 2. Same question. Utilize the provided data to determine the average rate of change of the number of bacteria measured in bacteria per year from 5 to 11 years. Well, fortunately, we're given 5 to 11 years, so that makes life easier. Express your answer as a decimal approximation and show the computations that lead to your answer. Normally, when you think average rate of change, you think f of b minus f of a over b minus a, right? Well, the same thing's going to happen here, except I'm going to use b's and t's. But I'm still going to use little b's and little a's. So this is the part that counts. That blue part doesn't count. I'm going to write out b of b minus capital B of a over b minus a. Okay, now I know what these are. These are going to be my B and my A, so you're going to be 5 and 11, but let's do 11 minus 5 in that order. Let's do 11 minus 5. I don't know why I would put it the other way. No. Yay. B of 11, I'll deal with in a second, minus B of 5. Now we know what those are. B of 11 was 800 minus b of 5, we know is 200 over 6. So you become 600 over 6, which becomes 100. So this is going to be measured in bacteria per year. It's going to be an increase of 100 bacteria per year. Now, that's just the average rate of change. We already know very well from the previous problem that this is an exponential guy, so it's probably going to look something like that, but this is asking you to find what that is right there, find the slope, and the slope is 100 bacteria per year. So, interesting problem. Use the average rate of change found in 1, which is 100, to estimate the number of bacteria for t equals 14 years. Show the work that leads to your answer. Well, we have 11 years, and 11 years is 800. So the work that I'm going to show is the fact that 14 is 3 more years more than 11 more, and I'm going to multiply that by 100. That's going to end up being 1,100 bacteria. So I didn't show a ton of work. I'm not sure what other, unless you want to describe or explain what's going on and say, I am adding 3 because that's 3 years after 2000, whatever. I'm always very paranoid where I like to show or write more than necessary. I don't know if they'd accept something like this. Maybe they would. I'm sure they would. But if you're always paranoid, just add more. Just make sure you don't make a mistake. The average rate of change found in I can be utilized to estimate the number of bacteria during year t for t is greater than 15 years. Will these estimates obtained using the average rate of change be less than or greater than the number of bacteria predicted by the model B during the year t? So, okay. Oh, and I only care about 15 to 25 years, not including 15. All right, so this is what I have to do. I have to compare what I got in part 2 of part A on the previous slide. And if you remember, that exponential function was b of t equals 62.996 times 1.260 to the t. That's my exponential guy. Now, my linear guy can be found by saying, all right, well, my slope is 100. So y equals 100x. I don't know what my y-intercept is, but if I take one of these points up here, like the point that I just came up with, what was that? 1010. If I take a point like that and plug it in, I get 1010 equals 100 times 14 plus b. You become 100,000 or 1010 equals 1400 minus 1400 minus 1400. B is equal to negative 300. So the linear equation that I get that is supposed to do a good job predicting data after 15 years is going to be y equals 100x minus 300. So what I need to do is I need to graph u and I need to graph u on the same graph. What I want to do is I want to compare what's going on between 15 and 25 and see which one, or see if the average rate of change, see if the linear one is less than or greater than. So again, I'm going to get a picture like this, right? And I don't know what my line is going to look like, but I need to find out, is my line greater than the exponential guy or is my line less than the exponential guy? And that'll be my answer to that. So let's run back to our calculator and figure that out. Okay, so let's graph them both. Like I said before, it sure would have been nice if I stored the exponential function, but since I'm going back and forth to my thing in the calculator, it deletes everything automatically. If you were able to store it, good. It would look like this, 62.996. And of course, if you did store it, it's going to give you a whole lot more points, but oh well. Times 1.260 to the t, so to the x. That's my exponential function. It's going to show up in blue. My y function is going to be y equals, or not my y, my linear is 100x minus 300. If I hit graph, I'm not near at all where I want to be. Okay, now what I care about, first off, is a window between 15 and 25. First, I need to see where these intersect. So I'm going to zoom out until I can see where they intersect. Not yet. Zoom out again to see where they intersect. That might do it. Okay, now it intersects like way up here. So what I'm going to do is I'm going to set my window to 15 to 25 because that's what I care about for my x values. And why don't we change my y min to 50 and just see what happens. Well, that's unfortunate. Let's zoom out again. Enter. Okay. So let's change my window to, let's do 100. Let's change this again from 15 to 25. And that's again unfortunate. So let's zoom out one more time because I'm trying to get the y's. All right. So what is this? What is this x value? Oh, the x value, hold on. The y value, okay, so the intersection here happens at 196. Okay, so let me see. Where does it, okay, okay. Let's do this. Let's go up to 500. I think I got it. Let's go up to 500. And by the way, this is kind of like a good thing that this is happening, that I'm like testing stuff out. If you're like, zoom fit, that might be useful, but it's too late. Let's change this one last time, hopefully, please, Lord, to 15 to 25. Hit graph. And how is this still not working? Am I still too low? What if I made this 1,500? Just overdo it. Hey, so now I don't see my exponential function. So let's make this 1,000 to 2,500. So much troubleshooting. All right. So there's my linear equation. There's my exponential equation. You can tell by the colors, but this is between 15 and 25. My linear equation is underneath my exponential equation between 15 and 25, no matter what. So it took all of that for us to figure out that our average rate of change possibility is going to be less than the model that we predicted back in part A. So after all of that, that's our answer. So let's go back and do that. All right, so after all of that, if you gave up on the video, I don't blame you. But what we saw is this guy, where the linear graph is below the exponential graph. So the average rate of change is less. The average rate of change, that's two ofs. The average rate of change will be less than. And to explain why, ... we'll write it out over here, because the graph of our average rate of change formula is below the B of t formula. So not a lot of room to write all this stuff out, but I was able to make it work. Sloppy, but I was able to make it work. So let's close this puppy out. Imagine, same problem. For which t value, t equals 8 or t equals 20, should the biologist have more confidence when using the model of B? Give a reason. All right, well, the model that we have is a model based off of numbers between 5 and 11. So it's going to be clear that t equals 8, okay, would be a better prediction because 8 lies in between our given t values of t equals 5 and t equals 11. Since t equals 20 is much greater than t equals 11 was the biggest one, our model may not show as much accuracy. Which makes sense. If you're going to predict something between 5 and 11, or predict something based off of 5 and 11, 8's literally right in the middle of it. 8's in the middle. So you wouldn't say, oh, yeah, I'm more likely to guess what's going to happen for 20 than for 8 because, you could graph these two and you can at least estimate what's going to happen in between. It's hard to estimate what's going to happen at t equals 20 because 20 is way down the road. So we did it. We did free response question number 2. Lots to do in this, lots to handle, but hey, I'm happy for us. I'm proud of you. So as always, I hope this helps. All right, free response question number 3, the traditional trig looking problem. I've seen a bunch of practice problems that have this picture and involve some type of oscillating figure, like whether it's a Ferris wheel spinning around or a bike pedal spinning around or a metronome going back and forth. In this case, we have a pendulum desk decoration that uses a magnet to keep the weight hanging at the bottom of a string swinging back and forth in all directions. So this was pretty popular when I was a kid way back when. You would get these things that you put a battery in and this thing hangs from the bottom and there's whatever the battery does creates some kind of electromagnetic field where this guy goes back and forth and back and forth and back and forth. So you can kind of assume, all right, well, the back and forth, that's where the waves come from. The weight reaches a maximum height of 3 inches off the desk and a minimum height of 1 inch off the desk. The pendulum sways back and forth, completing 3/4 of a cycle per second. The sinusoidal function h of t can be employed to model the height h with respect to time t. The pendulum weight is at its maximum height at t equals 0 seconds. Okay, so pretty much what we're dealing with is no calculator allowed. All right, if I were to, I'm not even going to draw a sinusoidal function. Draw the picture out. Usually I draw the picture out, but that seems to be done for me. Actually, you know what? The heck, I'm going to do it anyway. Let's take the information that we have and make ourselves a rough draft. Now, obviously, real life stuff, so all in quadrant 1. At the very top, we're at 3. At the very bottom, we're at 1, which puts us at a midline of 2. So right now we could start saying you would be my 3 and you would be my 2 and you would be my 1. Okay. The weight reaches maximum height of 3 and 1 inch off the desk. The pendulum sways back and forth complaining. I'll get there in a second. The sinusoidal function h of t can be okay. So it's at the maximum height at t equals 0 seconds. So it's already up here. Okay, which screams cosine, and this is going to go down and come back up. Okay, now it completes a cycle every 3/4 of a second, which means that's my period right there. Okay, my period is 3/4. Now, I don't know if I'm going to need this. Maybe I will, maybe I won't. But this is what I have already. Okay, I have this already. So the graph displays H and its dashed line midline for 2 complete cycles. Points A, B, C, D, and E are marked on the graph. No scalar axes are provided. Determine the potential coordinates T, H of T for these 5 points A, B, C, D, and E. All right, so right off the bat, we could do A as our maximum. So we could say that A is 0, 3. Okay. So you would be, this is where it gets a little complicated. So 0, 3, that part's pretty easy. B is going to be something 2. I'll get there in a minute. C is going to be something 1. I'll get there in a minute. D is going to be something 2. I'll get there in a minute. And E is going to be 3/4, 3. So that gives me E. Okay. Now, if you're like, whoa, 3/4, where did that come from? It completes a cycle at 3/4, which means the period is 3/4. Did I say 3/4? 3/4. All right, now we're going to have to do a little bit of math. Okay. So everything is going to be based on the fact that we start at 0 and we end at 3/4. So it hits its minimum at half of 3/4. It hits the midline here at 1/4 of 3/4, and it hits the midline again at 3/4 of 3/4. So if you followed what I just did there, B is going to happen at 1/4 of 3/4. Okay, so whatever the distance, this goes from 0 to 3/4. This is going to be 1/4 of it. So 1/4 of 3/4 is 3/16. My favorite Bible verse. So this is going to happen at the x value of 3/16 and a y value, or in our case, t and h of t, of 2. So 3/16 and 2. Now I hit the bottom literally halfway in between 0 and 3/4. So C's x value, or t value, is going to be half of 3/4. Okay, 1 times 3 is 3, 2 times 4 is 8. So I've got 3/8, 1. So C is going to be 3/8, 1. Okay. This is going to be 3/4 of the way to 3/4. So D, the t value, is going to be 3/4 of 3/4. 3 times 3 is 9. 4 times 4 is 16. That gives me 9/16, 2. So D is 9/16, 2. Now, the reality is there's an infinite amount of answers here, right? Because if I wanted to be a silly goose and start at 3/4, 3, I could have. But I didn't, because I'm not insane. So that's why it says potential coordinates. All right, so that's A is coming up with 5 points. Hooray! B is going to ask us to find the function. Oh, and like I said, this screams cos because it is cos. Determine the values of the constants A, B, C, D. Blah, blah. So again, my rough draft, right, had me starting up here at 3, midline at 2, and bottoming out at, well, let me put the dash line here, bottoming out at 1. Okay, we went down, bottomed out, and repeated at 3/4. Now, if you don't remember what means what here, A stands for amplitude. Okay. Now, the amplitude is half the distance from the top to the bottom, or it's the distance from the midline to the top. Okay, so the numbers are friendly enough where we could say, oh, okay, well, the amplitude is just 1, and you would be correct. Now, if you had to do some math because the numbers weren't pretty, the way you could find the amplitude is you would do 3 minus 1, the maximum minus the minimum, divide that by 2, and you would just get 1 anyway. Okay, but for this one, it's simple enough. If it's not simple enough, maximum minus minimum, divide by 2. There you have it. B stands for the frequency. Now, the frequency is found by taking 2 pi, because cos's period is 2 pi, and dividing it by the period that you have here, which is 3 over 4. So frequency is 2 pi over your period. My period is 3 over 4, so let's multiply the top and the bottom by 4/3, multiply the top and the bottom by 4/3. You cross out, you cross out, you cross out, you cross out. As tempting as it is to look at the 2 and 4 and think something crosses out, it doesn't. So I have 8 pi over 3. So B is going to be 8 pi over 3. Pretty gross, but that's what it is. C is a horizontal shift where you move left or right. Well, since I'm dealing with cosine, and regular old cosine looks like this, starting up here and going down there, I have the same exact behavior. So I have no horizontal shift. So my horizontal shift is nothing. Okay, D is going to be my midline or vertical shift. Whenever you think sinusoidal stuff, think midline, and my midline is 2. So if you're thinking, oh no, let's write out the formula and circle that. Don't do that, because they don't want you to write out the formula here. They just want you to figure out what A, B, C, and D are. So let's rewrite those out so they're nice and pretty. A is 1. B is 8 pi over 3. C is 0. D is 2. And that's part B. Part C has us referring to the graph in part A. Great. So I have that back. Let T sub 1 denote the T coordinate of point B. So you are also T sub 1. And T sub 2 denote the T coordinate of C. All right, so that's T sub 2. Within the interval T sub 1, T sub 2, which of the following statements accurately describes H? H is positive and increasing. Okay, so hold on, time out. Let's break this down. Let's remember exactly what we're dealing with, because it's giving me options about positive, negative, stuff like that. Remember, this is a pendulum swinging back and forth. Okay, it's up in the air in positive land. Okay, so you're 3, you're 2, you're 1. No matter what happens within this interval, so they're basically saying, what's happening between here and here? Well, between here and here, no matter what, we're positive because we're above ground. This is a pendulum swinging in the real world. So we're above ground, and no matter what, it's going to be positive. Okay? Now, what else is going on here? In this case, it's decreasing because it's going down and to the right. So this is positive and decreasing, which gives us B. Pretty simple answer. Okay? Nothing crazy that we have to lose sleep over. Okay? Why they're making us do T sub 1 and T sub 2, I have no clue. Why couldn't they just stick with B and C? I have no clue. I didn't make the problem. Actually, I did. Describe the change in the rate of change of H within the interval T sub 1 and T sub 2. And if you're thinking, rate of change, let's whip this puppy out. Yes, I can do this. Let me get the numbers from the previous thing. If you're thinking that, you're doing it wrong. They are saying the change in the rate of change. What that means is, if it's like, you're basically saying this is concave up and decreasing. So what you're saying is the change in the rate of change is going to have me describe what decreasing on concave up means. That's what they want. Change of rate of change is something like it's increasing at a decreasing rate, or it's decreasing at a decreasing rate. Whatever going down on concave up means. Concave up means the rate of change is increasing rate. Probably terrible English there. Decreasing at an increase, or whatever at an increasing rate. Okay, so increasing rate. What this is doing is this is decreasing. So the change in the rate of change is decreasing, in other words, going down and to the right, at an increasing rate. That's the part that means concave up. So it's decreasing at an increasing rate, going down, concave up. Okay, if I were to answer this one, you would say that's increasing at a decreasing rate because it's increasing on concave down. So it all is dependent on what you're talking about. But in this case, that's that. So 3 here had 4 parts. So I would like to imagine that the way it's graded is probably dependent on you showing work or you explaining, or the fact that we had to do 5 points on the one part. But yeah, that's 3. So that's free response question number 3. No calculators, lots of science stuff. Expect to see something like that. Like I said, in almost every single free response practice problem, I ran into this picture right here. Almost every single one, you run into this picture. Does that mean you're going to run into the same exact problem? No, but I would bet some money that you're going to be given some type of oscillating thing that maybe goes around in a circle or goes back and forth, and you can answer questions that we just saw. So be ready for something like that. Okay? That was fun. Hope this helps. Okay, don't adjust your YouTube, okay? This is free response question number 4. Before you do free response question number 4, they're going to give you a set of rules. The first 2 are kind of obvious. Assume things are real numbers, check. Trig stuff is measured in radians, check. Now, the third one is you will be given things that should be simplifiable. If you can simplify them, simplify them. For example, log base 2 of 8 can be written as log base 2 to the third. Base 2 cancels out, you get 3. You should be able to do that. Don't leave that like that. Cosine of pi over 2 is the x value of pi over 2, which is 0. You can simplify that. And the inverse sine of root 2 over 2 is the y value where you get root 2 over 2, which is pi over 4 and 3 pi over 4. So you can do those, guys. Don't leave your answers looking like that if you can keep going. All right. The fourth bullet says you can simplify these guys too. Like, don't be stupid and say, oh no, let's leave it as 2x and 3x. Oh no, let's not change it into that. Oh no, let's not change it into that. Oh no, let's not take the fact that if we add ln's, we multiply the inside. Simplify them if you can. Now, if you're not allowed to use a calculator. So obviously, you're not going to be expected to know what ln of 15 is, but you are going to be expected to combine things, add the exponents, subtract the exponents, combine like terms whenever you can. And for each part, show your work. There we are. So here we are. We're going to be given a bunch of algebraic situations that we're going to have to answer based off of the things that we're given. Okay, so this is part A, 1 and 2. We are given f of x. We're given g of x. 1 asks us to solve x if f of x is 6. So I'm going to take this guy right here, and I'm going to set 6 equal to ln of 9x squared. Now, first things first, I have ln all by itself with some stuff in the middle. I always like to take the e to the of both sides. I know it's not the grammatically most correct thing in the world, like that sentence I just said was, but that's what I like to do. If you would rather just write it out in exponential form, fine. It's the same thing. E to the ln of x is 9x squared, and you end up with e to the 6. Don't get your calculator out. You're not allowed to use one. I need to get x all by itself. Divide by 9, divide by 9. That crosses out. So you have e to the 6 over 9 equals x squared. Now, in order to get x all by itself, you have to square root both sides, and do not forget your positive or negative. Okay? Now, before you're like, I can't do anything, sure you can. You could do 2 things, and let me write it over here because I'm out of space. You could do 2 things. The square root of e to the 6th is asking what times itself is e to the 6th? E to the 3rd. Easily, what times itself is 9? 3. And you have plus or minus e to the 3rd over 3 equals x. Wait a minute. Can I take this guy and plug it into that guy and have it work out? Usually when I have negatives and ln's and stuff like that, I'm not allowed to do it. Well, I have news for you. You are allowed to plug in the negative, because before you take the ln, you plug in negative something and then square it, which makes it positive. So my answer is both positive or negative e cubed over 3. Now, obviously, we don't have a calculator. You can't simplify that. You can't do anything else with that. That is going to be our guy, and that's what we're sticking with. Okay, so kind of a tricky problem, but, we did it, and I'm proud of us. Okay, part 2 of part A has me setting this guy, which I know it's kind of faded, but you have 4 to the x plus 1 over 4 to the 5th equals, what was it, 16? Now I know what 16 is. 16 is 4 squared. And while I'm at it, why don't I multiply both sides by 4 to the 5th? Why don't I multiply both sides by 4 to the 5th? So I have 4 to the 5th times 4 squared equals 4 to the x plus 1. Just like we saw on this slide that told us all the rules that we were supposed to use, whenever you multiply terms of the same base, you add the exponents. And if you're like, what do I do? Should I get logs? Nope. If you have 4 to the stuff equals 4 to the stuff, set the stuffs equal to each other. So 4 to the 7 equals 4 to the x plus 1 means 7 equals x plus 1. Because you would log base 4 both sides, make the 4's go away, and this would just happen anyway. Subtract 1, x is going to equal 6. There's no rules here saying that I can't do this. And yeah, this kind of makes sense. I mean, if you were to go up here and say 6 plus 1 is 7, so 4 to the 7th over 4 to the 5th equals 4 squared, which is 16, which is what I'm supposed to get. Check, check, checkaroo. Now, checking this is not going to be near as friendly, but you could, if you wanted to, just trust me on that one. I did it right. Just trust me, please. I did it right. All right. All right, so what we have is h of x equals 6 log base 3 x plus 1, 4 log base 3 y plus 1, minus log base 3 z minus 4, and j of x is some trig-looking thing. One says express h as a single logarithm. Ooh, I like these. Whenever you're adding and subtracting logs of the same base, which, by the way, we are, step 1 that you always want to do is deal with the coefficients. If you have a coefficient, you can simplify that by making it an exponent. So you become log base 3 x plus 1 to the 6th power plus log base 3 y plus 1 to the 4th power, and nothing happens with u, minus log base 3 z minus 4. Then what you would want to do is organize all the pluses together and all the minuses together, and that's already taken care of. Step number 2 is if you add logs of the same base, multiply the inside. So this becomes log base 3. I'm going to put a nice little bracket here. X plus 1 to the 6th times y plus 1 to the 4th. We're going to leave it like that because I can't imagine we're going to be expected to FOIL this out 6 times, that out 4 times, then do a train wreck of a problem. I think we're okay leaving it like that. You're still going to subtract log base 3 z minus 4. Now, when you subtract logs of the same base, you divide the insides. So last but not least, our single logarithm is going to be log base 3, x plus 1 to the 6th, y plus 1 to the 4th didn't change. That's going to be over z minus 4 in an unnecessary parentheses. But now we have everything in a single logarithm. Hooray! I love it. I love it. And that's I. Double I is going to have me express this as a single trigonometric function. All right, whenever you're dealing with things that involve sine, cosine, secant, tangent, cotangent, cosine, you're going to want to change every non-sine cosine thing into its sine cosine version. So sine doesn't change. We still have 1 over sine x. Cotangent, however, is cosine x over sine x. Okay, so if I were to make believe that that's over 1, I know that that simplifies. So that leaves me with 1 over cosine x. Now, if you're thinking, that seems good enough to me, that is a single logarithmic function. Yeah, well, that 1 up in the numerator upsets me so. So remember, 1 over cos x is the same as secant x. So that's going to be our guy there. Just like that was our guy there. I love these. Oh, I love them so much. I love the algebra versions of these things. It just fills me with glee. This, on the other hand, is probably not going to fill me with glee. But we'll see what happens. Let k of x equals 6, the inverse cosine of x root 3, and m equals 3 inverse sine of root 3 over 2. Find the value of x in the domain of k that makes k of x equal m of x true. So I got to set these puppies equal to each other. Gross, 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 gross. All right, so I've got 6 inverse cosine x root 3 is equal to 3 inverse sine of root 3 over 2. Okay. I could divide everything by 3 if I wanted to. Might be helpful. I don't know. Maybe, maybe not. So that gives me 6 cos inverse sine of x root 3. That equals the inverse sine of root 3 over 2. Now, I know what the inverse sine of root 3 over 2 is. The inverse sine of root 3 over 2 is the y value on the unit circle. That gives me root 3 over 2, and that is pi over 3. So you become pi over 3. Okay? So I now have 2 cosine inverse x root 3 of both sides. I can divide both sides by 2, which kind of seems counterproductive. By the way, that's the same thing as multiplying by a half. So again, kind of seems counterproductive to what I did before. But now I have the inverse cosine of x root 3 equals x, or pi rather, over 6. Now, I need to somehow unlock that x. Now that I have all this cos stuff all by itself, I need to get rid of that inverse cosine. Well, just like we would use inverse cosine to get rid of cosine, I could use cosine to get rid of inverse cosine. It works the same way backwards. Okay, so you cross out, and we're left with x times the square root of 3 equals the cosine of pi over 6. I know what the cosine of pi over 6 is. The cosine of pi over 6 is root 3 over 2. I can divide both sides by root 3. So divide both sides by root 3. Okay, which, by the way, is the same thing as multiplying both sides by 1 over root 3. These cross out, and you get a half. X equals a half. So was this part fun? No, absolutely no. And this, again, is one of those things where the kids who get 5s will get that right. So great. You know, you're not expected to get every single problem on an AP exam correct. So if you get to this point at the very, very, very end of the test after 4 multiple choice problems and 4 free response questions, and you're losing your mind and you're going insane, and if you look at that and you're like, nah, I don't blame you. But you can do it. Put your mind into it. This concludes the ultimate GOAT AP Precalculus Practice Test version 1.0. I'll probably make a 2.0, but this is the first one, so thanks for watching, and as always, I hope this helps.